Welcome back to Sleep Nova. Sit back, relax, and enjoy the show. Look up on a clear night, far from the city lights. Above you stretches an endless dark ocean sprinkled with stars. The longer you gaze, the more stars appear, as if the universe is revealing a secret tapestry. Each star is a sun, distant and powerful. Our own sun is just one among hundreds of billions of stars in our galaxy. And our galaxy, the Milky Way, is one among trillions. In fact, astronomers estimate there may be 2 trillion galaxies in the observable universe. Try to imagine that. 2 trillion island universes, each brimming with stars beyond counting. If you could snap your fingers and count one galaxy per second, you'd be counting for over 65,000 years just to list them all. Within those galaxies are countless worlds. Some scientists say as many as 6 billion Earth-like planets may orbit stars in our Milky Way alone, and perhaps 12 quintillion across the cosmos. 12 quintillion Earths, 12 quintillion possibilities. The scale of space truly defies comprehension. It's a void, a vastness, but also a canvas of nearly infinite possibilities. Floating on a tiny rock called Earth, we humans have always felt small under this sky. Tiny, yet special, because we can ponder it. We can ask, what is all this? What is the nature of space, of reality? How amazing that the universe is comprehensible enough that we can study it, yet mysterious enough to inspire wonder. As the famous astronomer Carl Sagan once said, the cosmos is within us. We are made of star stuff. We are a way for the universe to know itself. We are made of atoms forged in long, dead stars, now come alive to gaze back at the sky. Through us, the universe questions its own existence. And one of the most profound questions we can ask is, are we even real? Could all this enormity, this grand cosmos, be an elaborate illusion or construction? Could we, our lives, our planet, our universe, be part of a grand cosmic simulation? That question sounds like science fiction, yet it has leapt from the pages of novels and movie scripts into serious scientific and philosophical debate. What if our reality is not the base reality? What if it's a program, running on some unfathomably complex computer, created by entities beyond our realm of existence? It's an idea that can feel both thrilling and unsettling, the simulation hypothesis. In essence, this hypothesis suggests that what we perceive as the physical universe, including space and time, might be an artificial simulation, like a high-resolution virtual reality designed by an advanced intelligence. In other words, maybe we are living in someone else's computer program. Pause for a moment and really consider that. The ground beneath your feet, the air you're breathing, the light from those distant stars, could all of it be code? If it were true, if everything we know is part of a simulation, how would we know? Would it even matter to us inside it? And who, or what, might be the programmer of the cosmos? These questions take us to the edge of what science can speculate and what philosophy can ponder. They force us to confront the nature of reality from a perspective that is both deeply cosmic and intensely personal. Tonight, we'll embark on a journey through this maze of ideas. We'll wander the vastness of space, marveling at its wonders, and we'll delve into the simulation hypothesis, examining why some prominent thinkers believe it might be true and why others remain skeptical. We'll touch on ancient philosophical puzzles and cutting-edge scientific experiments. We'll meet the scientists and philosophers wrestling with these questions, from those studying the quantum underpinnings of reality, to technologists pushing the boundaries of virtual reality, to philosophers questioning whether real and simulated are even meaningful distinctions. Along the way, we'll peer into the very code of the universe and see if there are hints that reality has a designer, and we'll imagine what it would mean for our lives, our purpose, our future, if we are indeed characters inside a grand cosmic simulation. This idea, questioning the reality of reality, is not entirely new. Long before computers and simulations, humans sensed that the world might not be exactly as it appears. Over 2,000 years ago, the Greek philosopher Plato proposed a famous allegory. Imagine people who have lived chained in a dark cave all their lives, Plato said, facing a blank wall. All they ever see are shadows cast on that wall, shadows of objects behind them, objects lit by a fire. Those shadows are their entire reality. They give them names. They think they're real things, but they're just projections, mere silhouettes of something truer. One day, a prisoner is freed and stumbles outside into the dazzling sunlight. For the first time, he sees the full, rich world beyond the cave and realizes the shadows were just a pale imitation of reality. Plato used this allegory of the cave to discuss knowledge and enlightenment, but it resonates eerily with the simulation idea. If we are like those cave prisoners, then our day-to-day world might be the shadow play, while the true reality exists outside our current perception. Could it be that we are living in a cave of sorts, seeing shadows and mistaking them for the whole of existence? Across cultures, similar notions appear. In ancient Chinese philosophy, Zhuangzhou wrote of a vivid dream in which he was a butterfly fluttering about. In the dream, he was happy, unaware of any other life. When he awoke, he found himself lying in bed as a man, but then he wondered, was he a man who had dreamed he was a butterfly, or a butterfly now dreaming he was a man? This butterfly dream story captures a deep puzzle. How can we know if our experience right now is real, or some kind of dream or illusion? Likewise, in Hindu philosophy, the concept of Maya describes the world as an illusion, a sort of cosmic play. And the French philosopher René Descartes, in the 17th century, famously imagined an evil demon that could be tricking him with an illusory world, an early pondering of a virtual reality created to deceive the senses. Descartes realized the only thing he couldn't doubt was his own mind's existence, which is not so far from the simulation question. If everything was simulated, the one thing we might be sure is real is our own consciousness experiencing it. We humans have a long history of questioning reality, but the simulation hypothesis, as we discuss it today, took these age-old questions and reframed them in the context of modern technology and cosmology. It's as if the ancient philosophical doubts met the era of computers and video games and found a new form. A key moment in popular culture was the release of The Matrix in 1999, a film that riveted audiences with its depiction of humans unknowingly trapped in a perfectly simulated world. People plugged into a virtual reality, living in a shared illusion while their bodies lay elsewhere, asleep. The Matrix wasn't the first story of its kind, but it presented the idea so powerfully that it became a cultural touchstone for this concept. Suddenly, the question, what if we're in a simulation, moved from esoteric philosophy to everyday conversations. After watching Neo choose between the red pill and blue pill, a whole generation had a reference point for discussing the nature of reality. Just a few years after that film, in 2003, a philosopher named Nick Bostrom at Oxford University gave the simulation idea a rigorous academic form. Bostrom wrote a paper with a title that cuts straight to the core: Are you living in a computer simulation? In it, he proposed a sort of logical argument, a trilemma. It goes something like this. 1. Almost all civilizations at our stage of technological development go extinct before they ever become technologically posthuman. In other words, maybe it's incredibly rare to survive long enough to create the kind of computing power needed for world-sized simulations. 2. If a civilization does reach that advanced stage, perhaps almost none of them would be interested in running simulations of minds like their ancestors. Maybe it's simply not done, whether for ethical reasons or lack of interest. 3. If the first two propositions are wrong, then the number of simulated conscious beings would far, far exceed the number of original beings. And if that's the case, the odds are that we ourselves are among the simulated minds, not the original biological ones. Bostrom argued that at least one of those three must be true. Either we're doomed to never reach that advanced stage, or we'll reach it, but never simulate worlds with conscious beings, or we're almost certainly in a simulation right now. Importantly, if you think there's any significant chance that advanced civilizations would run such simulations, then you have to admit the possibility that we might be in one. To put it another way, unless we go extinct or never bother to use our future computers this way, it's quite likely that reality as we know it is a digital illusion. That's the unsettling logic Bostrom presented. He even concluded, somewhat playfully yet provocatively, that the belief that there is a significant chance that we will one day become posthumans who run ancestor simulations is false, unless we are currently living in a simulation. In simple terms, we can't have it both ways. We can't both expect our descendants to create loads of simulated worlds and also assume we're in the one real world. If creating simulated universes becomes possible and common, then statistically, our own reality is probably one of the many simulations rather than the one original. This argument hit the scholarly world like a jolt. It was a serious professor, not a Hollywood director, suggesting this mind-bending scenario in earnest. And it came at a time when computing power was growing exponentially, and our own simulations, think computer games, virtual reality experiments, AI programs, were becoming more impressive every year. Bostrom's paper gave a sort of credibility to an idea that, until then, was mostly science fiction. It moved the conversation into journals and conferences. People began to debate, not just, could this be true, but what evidence would there be, and how would this change things? It didn't stay in academia. The idea spilled out into tech companies, into late-night dorm room discussions, into Reddit forums and YouTube channels. Even major public figures started taking it seriously. Perhaps the most famous among them is entrepreneur Elon Musk, known for his ventures in electric cars and space travel. Musk has repeatedly talked about the simulation hypothesis. In 2016, speaking at a conference, he put it in his characteristically blunt terms. There's a 1,000,000,000 chance we're living in base reality, meaning he thinks the odds that our reality is the original reality are almost zero. In other words, Elon Musk believes it's extremely likely that we are living in some kind of computer simulation. That statement grabbed headlines around the world. Here was one of the most high-profile innovators on the planet, casually asserting that everything we experience might be artificial. Musk's rationale was simple. Look at the trajectory of video games. In the 1970s, we had Pong, 2 rectangles and a dot. Today, we have hyper-realistic 3D simulations with millions of players in richly rendered worlds, and virtual reality technology that can trick our senses for a time. Given another few decades or centuries, the argument goes, it's inevitable that our technology will produce simulations indistinguishable from reality. If we have that potential, then perhaps some other civilization in the universe already achieved it. And if even one civilization did, the number of simulated universes could be astronomically large. So from Musk's perspective, the math makes it hard to believe we are the one lucky draw that is actually real. He's not alone. Astrophysicist Neil deGrasse Tyson, a science communicator who hosts TV shows and podcasts, has said he thinks there's a very high chance the universe is a simulation. At a debate in 2016, Tyson suggested the likelihood might be better than 50-50 that we live in a simulation. Philosophers like David Chalmers and physicists like Max Tegmark have also entertained the idea in public discussions. Suddenly, the simulation hypothesis has moved from a fringe idea to a topic discussed by scientists at prestigious forums. In fact, the American Museum of Natural History held an entire panel debate on it, with experts from different fields. One journalist described that debate noting that philosophers, physicists, technologists, and, yes, comedians are all grappling with the idea. It has, in a sense, become mainstream speculative thought. But let's step back a moment. Is there any evidence for this idea, or is it all circumstantial and philosophical? Why would serious people even consider that we might detect the telltale signs of a simulation? To explore that, we need to delve into the nature of physical reality itself, into space, time, and the quantum realm, and see if our universe behaves the way we'd expect a base reality to behave, or if it has quirks more suggestive of a programmed environment. First, consider the nature of space. We usually think of space as simply emptiness. You might picture the void between stars as a silent, cold nothingness. But in physics, space is not truly empty. It has properties. It can bend, ripple, and even boil, with tiny particles popping in and out of existence. According to Einstein's theory of general relativity, space is like a fabric that can stretch and curve. Massive objects like stars and black holes warp this fabric, which is what we feel as gravity. Space, in this view, is dynamic. It's not just an empty stage where things happen, it's part of the actors. When we observed gravitational waves from colliding black holes for the first time in 2015, it was literally space itself trembling, like a pond rippling when a stone is dropped. This is a far cry from the simple nothingness one might assume space to be. Now, zoom down to the tiniest scales, and space gets even weirder. In quantum mechanics, even what we call a vacuum seethes with activity. Particles and antiparticles can spontaneously appear in pairs, exist for a fleeting moment, and annihilate each other. A phenomenon allowed by the quantum rules, as long as it's brief. This isn't science fiction. It's been experimentally observed. If you think about it, this is almost like the universe has a constant background computation running, even when nothing is there. It's as if the simulation never truly idles. There's always some processing happening in the vacuum of space, a constant quantum hum. What about the size of space? The observable universe, the part of the cosmos we can in principle see, extends about 46 billion light-years in every direction from us. We often say 13.8 billion years old, but due to expansion, the radius is larger in light-years, and that's just what's observable. Space could be much larger, potentially infinite. If a simulation were to recreate such a vast space in full detail everywhere, the amount of information would be mind-boggling. Could any computer, even one built by gods or advanced aliens, simulate 2 trillion galaxies worth of stars, planets, and particles? It seems intractable, but if we were inside a simulation, there might be ways to cheat and not simulate everything at once. Think of how video games work. When you're playing a game, the computer or console isn't rendering the entire game world at high resolution all the time. It's only rendering what the player is currently seeing or experiencing. Turn away from a scene, and the game might stop calculating it until you turn back. Some have suggested that a universe simulation might do something similar, only calculate details as needed. This ties into one interpretation of quantum physics that's frequently mentioned in the context of simulations: the idea that observation seems to play a role in how quantum events resolve. There's a famous experiment, the double-slit experiment, where particles are fired at a screen with 2 narrow slits. If you don't observe which slit a particle goes through, the particle acts like a wave of possibilities, going through both slits and creating an interference pattern on a detector screen, as if it interfered with itself. But if you set up a detector to watch the slits, the interference pattern disappears. The particle behaves like a single, well-defined object that went through one slit or the other. Simplifying a lot, the outcome changes depending on whether it's observed. To many, this suggests that reality decides on an outcome only when it has to, when an observation is made. This is a cornerstone of quantum mechanics, often summed up as the observer effect. Now, some physicists will caution that it's not that consciousness causes the change per se, just the interaction with a measuring device. But the philosophical interpretation lingers. Perhaps things aren't determinate until they need to be. If you were designing a simulation, that's actually a smart way to save resources. Don't calculate something until someone tries to look at it. In a way, the universe already behaves like that at the quantum level. It's as if there's a level of reality that's in potential form, a haze of probability, and it becomes concrete only upon interaction. Could that be the sign of a rendering engine at work? As Tyson and his comedian colleague Chuck Nice quipped on Star Talk, maybe that's why we have the speed of light limit in our universe. Perhaps the simulation doesn't allow anything to travel faster than light, because then you could get to another star or galaxy faster than the program could load the details. In their playful exchange, Chuck Nice suggested, maybe that's why we can't travel faster than the speed of light, because if we could, we'd be able to get to another galaxy before they can program it. And Tyson added with a laugh, so the programmer put in that limit. It's a joke, but it perfectly illustrates how a computational constraint could manifest as a law of physics. Our cosmic speed limit might be akin to the draw, distance in a video game, preventing us from moving too fast for the simulation to keep up. Let's think about other hints. Some scientists have looked for signatures of discretization in space, essentially evidence that space is not continuous, but made of tiny pixels or chunks, like a digital grid. If the world is simulated, it might be running on a lattice or grid at the smallest scale. In our current physics, we have the concept of the Planck length, which is far smaller than anything we can directly measure. It's often thought of as a scale at which classical ideas of space break down and quantum gravity might take over. If space were truly pixelated, the Planck length might be the size of the pixels. A few researchers have proposed experiments to detect this. Dr. Zohre Davoudi, a physicist at the University of Maryland, has discussed how, if space-time is discrete, there could be slight changes in how high-energy particles travel across cosmological distances. For instance, we might detect a tiny preferred direction or an upper limit in the energy of cosmic rays because of the underlying grid. Imagine if you tried to draw a perfectly straight, extremely long line on a pixelated screen. At some point, the discreteness might show anomalies. Davoudi specifically noted that if space-time is on a lattice for the simulation's sake, extremely energetic particles might not behave exactly as expected in a smooth continuum, possibly revealing a break in a symmetry-like rotation. So far, no such anisotropy in cosmic rays has been observed. If one were, it would be intriguing, though not absolute proof of a simulation. But the fact that physicists are even contemplating such tests shows how seriously the idea is being taken. Another striking piece of maybe evidence came from James Gates, a theoretical physicist known for his work in supersymmetry. Gates found something unexpected in the equations he was studying. Deep in the mathematical framework of certain supersymmetric models, he discovered equations that are identical to those used in computer error correcting codes. Error-correcting codes are algorithms programmers use to ensure data isn't corrupted. Basically, they help systems self-correct mistakes. They are, as Gates put it, what make browsers work, allowing digital information to transmit reliably. So, it was quite startling to find them knitted into the fundamental equations describing how particles and forces might work. Gates said, "I no longer can say that people like Max Tegmark are crazy." Upon realizing this, implying that seeing something so digital, looking in the bedrock of physical law gave him pause. He mused that finding such code in nature's equations, if nature weren't a simulation, would be an extremely unlikely coincidence. Does that mean the universe is a computer program? Not necessarily. It could be that our mathematics just happens to take that form, or perhaps there's a deeper reason for those codes that has nothing to do with actual computing. But it's tantalizing details like this that make scientists raise an eyebrow. It's as if you were walking through a forest and found a computer chip lying on the ground. you'd wonder, is there an intelligence at play here, or is it just an odd-shaped rock that happens to look like a chip? Cosmologist Max Tegmark, whom Gates referenced, has pushed an even broader idea, that the universe fundamentally is mathematical. Tegmark often points out that the more we study nature, whether it's the motion of planets or the behavior of subatomic particles, we find that mathematics describes it with uncanny precision. The laws of physics can be written in equations. They have symmetry and structure, much like a code. Tegmark's perspective is that perhaps the universe isn't just described by math, it is math in a very real sense. If one were a character in a video game, he notes, at some point you might notice the strict mathematical rules of your world and suspect there's an underlying code. Our scientists, by uncovering equations, might just be reading bits of the cosmic source code. This doesn't prove a programmer in the usual sense. Tegmark is careful to frame it as the universe being a mathematical structure on its own, but it certainly rhymes with the simulation narrative. After all, what is code, if not mathematics, implemented in a machine? So from the quantum behavior suggesting on-demand rendering, to potential spatial pixels at Planck scales, to literal error, correcting codes popping up in theoretical physics, the universe has some hints that tickle the mind. None of these are smoking guns. For every intriguing clue, skeptics can offer alternative explanations, but they add up to a picture of a universe that is surprisingly information-like. The physicist John Wheeler once coined the phrase "it from bit," meaning that at a fundamental level, everything may arise from binary choices, from information bits. More and more, our best theories of physics speak in terms of information. Black holes, for example, are often described by how they store information on their event horizons. Quantum entanglement is being investigated as the possible pixel glue of space-time itself in some modern theories. Scientists are exploring the idea that space-time geometry might emerge from patterns of entanglement, essentially from information networks. It's almost as if the universe behaves like a giant information processor. And if so, one can't help but ask, who or what is processing that information? Is it just the universe being the universe? Or is it a computer built by something beyond it? Now, let's take a step further out and look at a completely different line of thinking, the Fermi paradox and the eerie silence of the cosmos. In our opening, we talked about the vastness of space and the countless planets that likely exist. Given those numbers, many scientists believe that life, and eventually intelligent life, should have arisen in many places across the cosmos. Even if a fraction of those 12 quintillion Earth-like planets developed life, and a fraction of those developed intelligent civilizations, there ought to be many alien civilizations out there, some perhaps far older and more advanced than us. This reasoning is encapsulated in the Drake equation, which is a probabilistic formula to estimate the number of communicative civilizations in our galaxy. Depending on what numbers you plug in, you might predict anything from 0 to thousands of civilizations. But many reasonable estimates suggest the galaxy should be home to several at least, and the universe at large, many more. So physicist Enrico Fermi famously asked, "Where is everybody? If life is common, why haven't we seen any evidence? No confirmed signals, no spacecraft, no alien visitations that withstand scientific scrutiny. The skies are quiet and have been for as long as we've been listening." This puzzlement is what we call the Fermi paradox. Over the years, people have suggested numerous possible solutions. Maybe life is rare, or intelligent life destroys itself quickly, or maybe alien civilizations are out there but choose to hide or observe us from afar. One particularly mind-bending proposal is directly relevant to our topic. Perhaps we don't see aliens because the universe has been designed to appear empty to us. This is sometimes called the planetarium hypothesis. Imagine we are inside a giant virtual planetarium or terrarium, crafted to give us an illusion that we are alone. In 2001, science fiction author Stephen Baxter wrote an essay suggesting exactly this, that maybe advanced extraterrestrials, perhaps ones who reached a Type 3 civilization on the Kardashev scale, have created a simulation around us so that we perceive a vast, empty universe. They keep us in the cosmic equivalent of a snow globe. We look out and see stars and galaxies, but maybe the details beyond a certain point are all a projected illusion. Baxter wrote that our universe could be a form of virtual reality planetarium designed to give us the illusion that the universe is empty. In this scenario, the reason for the simulation is key. It might be to quarantine us or protect us. Perhaps they worry that if we knew about them, or if we encountered them, it would disrupt our natural development, or cause us to panic. Or maybe it's to protect themselves, ensuring we can't locate them. It's a wild idea, but it does answer Fermi's question in a creative way. We haven't seen aliens because our reality is constructed so that we won't. Whenever we point our telescopes out and listen for signals, the simulation dutifully returns a result of grand silence because that's its programming. If true, it implies our simulators are not necessarily our descendants, but could be alien beings in a higher level reality. They might be running a simulation of the universe and intentionally omitting themselves. It's like we're NPCs in a video game who aren't allowed to meet the game masters. Of course, if that's the case, what happens if one day we humans start reaching out into space in earnest? Baxter mused that maybe the simulation has built in limits to stop us. For example, the laws of physics that limit space travel could be intentional. The enormous cosmic distances and the finite speed of light act as barriers to keep us from ever leaving our sandbox region of the simulation. If somehow we got close to escaping, say we built ships that approach light speed, perhaps the simulators would intervene with some new obstacle. It's a bit like the Truman Show, where the main character tries to sail away from the island and literally bumps into the sky, which is a painted dome. Is our sky, our space, a painted dome in some sense? Hard to believe, and currently impossible to know. But it certainly fires the imagination. Now, before we get carried away, it's important to note that while some researchers find such ideas intriguing, they also acknowledge limitations and criticisms. For instance, can a simulation even be that large and perfect? One challenge is what we call computational complexity. If you were to simulate an entire universe down to the level of atoms or quarks, the amount of computing power seems unfathomable. We struggle to simulate even a tiny chunk of the physical world with our best supercomputers. Simulating the quantum behavior of a few dozen particles can tax our largest machines. In fact, researchers using quantum Monte Carlo simulations find that the complexity grows exponentially with the number of particles. They've pointed out that to simulate just a small piece of reality at full quantum detail might be effectively impossible for any practical computer, even one the size of a planet or a star. So skeptics argue, how could a simulator handle 10 Bow 80 particles, each doing their quantum dance? Well, proponents of the simulation idea respond that a simulator could use shortcuts. We already touched on one. Only simulate what's needed. Perhaps the simulating computer doesn't bother to calculate the interior of distant stars or the exact behavior of every galaxy unless it becomes relevant to the story. Perhaps it focuses on Earth and its vicinity, and everything else is painted in broad strokes, with detail filling in only when we look closely. Some have even speculated that things like quantum indeterminacy or chaos theory could be features that prevent us from ever predicting and thus compressing the universe's behavior. If the simulators are clever, they might not need infinite power, just very sophisticated algorithms that always stay a step ahead of the players. Another counterargument is Occam's razor. This is the idea that, all else being equal, the simplest explanation that fits the data is preferred. The simulation hypothesis is, to put it mildly, not the simplest explanation. It posits an entire additional layer of reality, with beings and technologies far beyond our own, all to explain a universe that we could otherwise just take as is. Physicist David Kipping performed a Bayesian analysis and initially found about a 50% odds for us being in a simulation, given no prior information. And he noted that, if humanity ever creates simulations of conscious beings, those odds would dramatically tip toward the simulation scenario. But Kipping himself has said that because the simulation idea is so elaborate, Occam's razor might count against it. Without evidence, why assume a complicated multi-layer reality when a single-layer reality works fine? He and others have likened it to a philosophical speculation that may not be testable, and if it's not testable, can it be considered scientific? After all, any evidence we find could be just features of the universe, not proof of external programming. The ultimate problem is falsifiability. We can't currently devise an experiment that would definitively tell us, yes, this is a simulation, or no, it's not. If the simulation is perfect, any result is just part of the simulation. As philosopher David Chalmers put it, there's certainly not going to be conclusive experimental proof that we're not in a simulation. Any evidence we could ever get would be simulated. In other words, a clever simulator could always tweak things to keep us guessing. So some argue, what's the point of even debating it if we can't prove or disprove it? Perhaps, they say, we should just proceed as though the universe is real. Lisa Randall, a prominent physicist, has expressed that she finds the simulation hypothesis pretty implausible and not very useful. We might as well keep doing science and not worry about being in a simulation. She remarked, "We don't know the answer, and we just keep doing science until it fails." If at some point our scientific understanding truly hits a wall that can only be explained by "we're in a sim," then maybe we'll reconsider. But until then, the hypothesis is more of a fun thought experiment than a practical guide. Randall also noted that thinking about such scenarios can still be valuable if it motivates us to ask interesting questions about physics we can test. In a sense, even if we don't buy the simulation theory wholesale, exploring it might spark new ideas or new ways to look at the cosmos, and that is certainly worthwhile. Now, let's imagine for a moment, what if we did discover evidence we're in a simulation? Or suppose one day an anomaly happens that simply can't be brushed aside. Maybe a message appears in the sky that can't possibly be natural, or we find an actual glitch in physics that is so specific it points to design. How would we react? Would it change how we live our lives? There are many science fiction scenarios about this. One could imagine society reacting with denial, or with a religious fervor, or maybe with panic, or conversely with relief. That explains everything. It's hard to know. Some thinkers have said it shouldn't change much on a day-to-day level. If you find out the universe is a simulation, the tree in your backyard is still a tree. The love you have for your family is still real to you. The taste of your favorite food is the same. You still have to go to work, avoid stepping in front of buses and all that. In fact, in a perfectly run simulation, you can't actually do anything outside the rules of the simulation, so you'd have to continue living by its laws. But psychologically, it could be a heavy realization. Would people feel less guilty about doing wrong, thinking, none of this is real, so what does it matter? Or would they feel more purpose, like, we're part of a planned creation, we better make our creators proud? Different individuals might react differently. Interestingly, the simulation hypothesis has a way of merging with traditional ideas of spirituality and religion. If there are creators outside our reality who made our world, how is that so different from concepts of God or gods? Some have pointed out that the simulation argument is like a technologically updated creation story. Instead of a supernatural deity, you have a super intelligent programmer. Instead of mystic heaven, you have another universe that hosts the computer. It reframes phenomena like an afterlife. As Dr. James Gates noted in that panel, if we are in a simulation, reincarnation might be literally possible. Our lives could be restarted or the program run again, effectively bringing everyone back to life. If you've ever played a video game, you know that dead characters can often respawn, or a saved game can be loaded to replay a scenario. In a simulation, maybe death isn't permanent. The data of your mind could be saved or copied. The simulation could also allow for things that look like miracles. Perhaps the simulators can intervene or tweak things now and then, which might appear to us as divine acts or anomalies. It's a whimsical parallel, but it does start to blur the line between science fiction and theology. In fact, Gates said that the simulation idea starts to break down a funny barrier between what people often think is the conflict between science and faith. Because here we have a scenario with creators, possibly an intention or purpose, and potentially even a form of life after death. Yet it's framed in a logically and technologically grounded way, rather than a mystical one. It's almost like a bridge between two worldviews. Of course, not everyone would agree with venerating simulator beings as gods. Philosopher Chalmers quipped that even if we were in a simulation controlled by higher beings, he'd refuse to worship the simulators. After all, they might be just scientists or gamers, not morally superior divinities. And if they allowed suffering in the simulation, one might question their ethics just as we question why a benevolent God would allow evil. Are we just an experiment? Entertainment? Education? Who knows what their motive would be? There's even a theory that maybe it's us, our future descendants, running ancestor simulations to study their own history, which raises all sorts of paradoxes and moral questions about creating conscious beings for study. Bostrom himself pondered on whether it would be ethical to run simulations of suffering. Let's entertain a positive angle. If we are in a simulation, maybe the simulators are benevolent. Perhaps we're a kind of long-term art project, being carefully tended. If at some point we're in danger, maybe they'd subtly steer things to save the project. Some people have humorously suggested that the lack of catastrophic asteroid impacts in recent times, or the fortuitous timing of certain events in humanity's past, could indicate someone wants us to reach a certain stage. That's highly speculative and arguably just human-centric storytelling. But it's true that the simulation idea can either make you feel extremely small or strangely important. Another fascinating speculation: what if we ourselves create simulations within this universe? If we build our own simulated realities populated by AI beings who think they're alive, then we'd have a nested simulation. Perhaps that's already happened. Maybe the simulators who built our world are themselves simulated by a higher level, and so on. This could lead to a chain of simulations within simulations. Tegmark pointed out a philosophical issue with Bostrom's argument. What stops an infinite regress of simulated worlds? If simulations become common, there could be many layers. But could it be simulations all the way down? At some point, there might need to be a base reality where the first simulation runs. If we're deep in a stack of simulations, our chances of reaching or understanding the true base reality are extremely slim. It would be like a character in a video game becoming aware of the game and then trying to figure out the world of the game developers by only exploring inside the game. They might get some hints, but can't break out of their level. Some tech visionaries have even talked about trying to break out of the simulation. There were reports that certain billionaires in Silicon Valley were funding research to find a way to detect or escape the simulation. It sounds like the plot of a movie. The rich and brilliant trying to crack open the sky of the Truman Show. While those specific stories might be exaggerated, it's true that the simulation hypothesis has captivated some of the most future-oriented minds. If you truly believed we're in a simulation, one radical idea would be to attempt to communicate with the creators. Maybe not by building a physical Tower of Babel, but perhaps by sending a clever message or creating a scenario within the simulation that stands out. Some have facetiously suggested that we should perform bold, unpredictable actions so as to get the simulator's attention. Max Tegmark, at the end of that debate, half-jokingly advised, "If you're not sure whether you're actually simulated or not, my advice to you is to go out there and live really interesting lives and do unexpected things so the simulators don't get bored and shut you down." That might be the best advice regardless of simulation status. Live an interesting, meaningful life, just in case someone is watching from above, and for your own sake if no one is. Now, we've journeyed through a lot, from the starry expanse of space to the subatomic quirks of quantum physics, from ancient philosophy to cutting-edge computational theory, from the loneliness of the cosmos to the possibility that we're not alone at all, but rather surrounded by an invisible infrastructure of a simulation. Through it all, one thing is clear: the line between reality and illusion is delicate. Whether or not we live in a simulation, pondering it forces us to appreciate reality's richness. If our universe is a simulation, it's a masterpiece of one. Think about it. The simulators would have created every coral reef, every nebula, every laugh, every tear, the taste of chocolate, the laws of gravity, the music of Mozart, the equations of Newton, the light of 1 billion trillion stars, and they gave us the tools, like science, to start to figure it out. That's quite something. And if this is not a simulation, if this is the one true reality, then it's even more incredible. It means from empty darkness and mindless matter, the universe evolved to a state where it can dance and think and wonder through us. We, tiny specks on a pale blue dot, can question the very fabric of existence. In the end, the simulation hypothesis is a mirror. Look into it, and it reflects our deepest inquiries. It asks how far our intelligence can go, how we distinguish truth, how we find meaning. It has us grapple with what-ifs that challenge our perception of time, space, and ourselves. Are we a cosmic accident, alone in an unconscious universe? Or are we characters in a cosmic play with hidden audience and playwright? Perhaps we'll never know for sure. Perhaps one morning, like Zhuangzi, we'll wake up and realize this was all a dream. Or maybe we'll venture out into space, among the real stars or the simulated ones, and gradually peel back the layers of reality. Until then, the best we can do is live fully and curiously. Simulated or not, this life is the one we have. If it's a simulation, maybe we honor it by being the most interesting simulation we can be. If it's base reality, we cherish the fact that we're part of something truly fundamental. In both cases, our experiences, our joys and sorrows, our aspirations, they matter to us and to those around us. As far as we're concerned, they are real. The philosopher Chalmers might remind us, even if all is a simulation, the simulation is our reality, so it's real to us. So when you next step outside on a crisp night and look up, consider the stars again. Each one could be a distant sun in a vast, real galaxy, or a pixel lit up on the canvas of a sky created for our benefit. Either way, let that sight fill you with wonder. The universe, be it natural or programmed, is majestic and mysterious. We find ourselves alive in the midst of it, able to ask grand questions. That is a privilege beyond measure. In a way, through our eyes, the universe gets to witness something too. A species growing from curiosity, reaching out for truth, striving to understand the infinite. Perhaps that's the point of it all, to wonder. Perhaps the ultimate cosmic experiment is to see if intelligent life can figure out its own reality, or at least learn to live harmoniously within it. We may not have the final answers, but we will keep searching, observing, hypothesizing. We will keep exploring space, both outer and inner, physical and virtual. And as we do, we carry in our minds the profound possibility that reality might be far more layered than it seems. It's a possibility that humbles us, but also elevates our imagination. Real or simulated, the stars still shine down, the night sky still calls to us. The mystery remains as deep and dark as space itself. And in that mystery lies beauty, because a universe without secrets, simulated or not, would be far less interesting. So let's embrace the mystery. Let's cherish the awe we feel when confronted with the cosmos. If we are in a simulation, then let's be the best characters we can be. And if we're not, let's be the best beings this universe can produce. In the end, perhaps it doesn't matter whether our reality is base level or virtual. What matters is what we do with the reality we have. As the great adventure of knowledge and existence continues, we remain, as always, explorers. explorers of space, explorers of ideas. We stand on the shore of the cosmic ocean, with the waves of the unknown gently lapping at our feet. Above us, the sky, real sky or manufactured dome, is full of stars. We feel small, yet connected to something vast. We feel the urge to reach out, to understand. And so we journey on, minds wide open, hearts alight with wonder. Who knows what we'll discover, what truths or illusions await? The nature of space and the mystery of the simulation hypothesis together form a story still unfolding. Stay curious, keep looking up, and remember, the universe is far more wondrous than any fiction ever conceived. Possibly because, in some way, it might be a fiction, crafted with care. Or perhaps because a simple truth underlies it all. Either way, it invites our curiosity, and that, in itself, is the grandest invitation we could ask for. Now that our main story is to a close, let's list some space facts. Imagine a place in the universe where a single spoonful of material weighs more than Mount Everest. Neutron stars, the ultra-dense remnants of massive stars, are so compressed that just 1 cubic inch of their matter would tip the scales at billions of tons. These stellar corpses are the densest objects known outside of black holes. Their magnetic fields are trillions of times stronger than Earth's, a city-sized ball of neutrons, spinning at hundreds of revolutions per second, crackling with radiation, isolated in the cold silence of space, a lighthouse of doom beaming through the dark. Step outside the airlock of the International Space Station, and something surprising happens. When astronauts return from their spacewalks, they often report a distinct smell clinging to their suits. Not the void itself, but the aftermath of exposure. The odor, burnt steak, welding fumes, a metallic tang. This is the scent of space, or at least how our senses interpret the byproducts of atomic oxygen interacting with spacecraft surfaces. It's the smell of the universe in motion, of particles colliding, of stars being born and dying. Venus, Earth's twisted twin, takes its time. If you were to stand on its blistering surface, where temperatures melt lead and clouds rain acid, you'd notice something even more bizarre than the heat. A single day on Venus, one full rotation on its axis, takes longer than an entire trip around the sun. That means its day is longer than its year. A planet where the sun rises in the west and sets in the east, crawling through a sky it barely crosses. Time stretches strangely on Venus, and so does our understanding of what makes a planet normal. Far beyond our galaxy, past swirling nebulae and clusters of galaxies, lies something extraordinary. Around a quasar, 12 billion light-years away, astronomers discovered a cloud of water vapor large enough to fill Earth's oceans. 140 trillion times. This ancient fog surrounds a supermassive black hole, glowing brightly with the energy of an entire galaxy. It's the largest and most distant water reservoir ever found. A cosmic oasis in the void, proof that even in the deep past, water flowed freely across the stars. The moon has always been our closest companion, our silent sentinel in the sky, but it's slowly drifting away. Every year, the moon moves about 1.5 inches farther from Earth. It may not sound like much, but over millions of years, it adds up. In the distant future, the moon will be too far to perfectly eclipse the sun. Total solar eclipses, those magical moments when day becomes night, will cease to exist. A celestial goodbye that spans eons, unnoticed in a single human lifetime, but profound in the timescale of the cosmos. Not all planets are tied to stars. Some wander alone. These are rogue planets, dark, cold worlds without a sun, flung into the abyss by gravitational chaos. Billions of them roam the galaxy like cosmic orphans, drifting endlessly through space. With no light to define their days, and no warmth to shape their climates, they remain mysterious. Some may harbor subsurface oceans, heated from within. Others may be completely frozen, locked in a stasis that has lasted since the dawn of time. They are reminders that not every world belongs to a system. Some just float in solitude. The Sun, though just one star among billions, is a giant in our own neighborhood. It holds 99.86% of all the mass in the solar system. That means everything else, every planet, every moon, every comet and asteroid, is just debris in comparison. Even mighty Jupiter, the king of the planets, is barely a drop in the solar ocean. The Sun dominates not just through heat and light, but by sheer gravitational force. It commands the dance of planets, holds the icy edges of the Kuiper Belt in place, and bends the very fabric of space and time around it. Speaking of time, it's not as steady as it feels. In places of intense gravity, like near a black hole or even on a planet like Jupiter, time flows more slowly. This is not science fiction. It's the bizarre truth of Einstein's general relativity. Gravity warps space-time. The closer you are to a massive object, the slower time passes for you. Live your life orbiting a black hole, and you might experience minutes while years pass outside. Time is elastic in the universe, flexible, strange, and deeply tied to gravity. High above Earth, satellites orbit in perfect balance. But there's something else out there too: space junk. The modern sky is littered with remnants of human ambition, dead satellites, rocket parts, tiny fragments of old missions. Over 170 million pieces of debris now race around our planet, many traveling at speeds faster than a bullet. A single screw could punch through a spacecraft like shrapnel. It's a growing cloud of chaos, and one that we'll have to reckon with if we hope to keep exploring the stars. On the outskirts of the solar system, beyond Neptune, lies a vast and icy graveyard known as the Oort cloud. It's never been directly seen, but we know it's there. A shell of frozen objects encasing the solar system like a bubble. Some comets we see in the sky begin their journey here, drifting for millions of years before the sun's gravity gently tugs them inward. The Oort cloud may stretch halfway to the next star, holding the leftovers of solar system formation, ancient time capsules frozen in deep space. Jupiter is more than just the largest planet in our solar system. It's a shield, a protector, a cosmic vacuum cleaner. Its immense gravity pulls in comets and asteroids that might otherwise strike Earth. Without Jupiter, life here might never have had a chance. But this gas giant has secrets of its own. Beneath its swirling clouds lies a core of metallic hydrogen, a state of matter so exotic it can only exist under immense pressure. Lightning storms larger than Earth rage across its surface, and its iconic Great Red Spot is a hurricane that's been raging for centuries. Saturn's rings are perhaps the most visually stunning feature in the solar system, but they're young, maybe only 100 million years old, and they're vanishing. Slowly, inexorably, the rings are falling into Saturn, pulled down by gravity and magnetic forces. What once dazzled stargazers may one day disappear entirely. The rings are made mostly of ice, ranging in size from dust grains to bus-sized chunks. They're delicate, temporary, a reminder that even beauty on a planetary scale can be fleeting. And then there's Pluto. Once a planet, then demoted, yet still beloved. This distant world has a heart-shaped glacier on its surface and mountains made of water ice. But what's more fascinating is what lies beneath. Scientists believe Pluto may have a subsurface ocean, liquid water under layers of rock and ice. In the frozen reaches of the Kuiper Belt, warmth can still exist, not from sunlight, but from radioactive decay deep within. Even in the coldest places, the potential for life may remain. Let's drift even farther, to a galaxy not so different from our own, one of many. The observable universe contains more than 200 billion galaxies, and each of those galaxies contains hundreds of billions of stars. That means there are more stars in the universe than grains of sand on every beach on Earth. Yet despite this overwhelming abundance, the night sky feels quiet, peaceful, but it is anything but empty. It is alive with movement, with birth and death, with explosions and silence, with radiation and dust. Black holes, cosmic monsters that devour light itself, sit at the heart of many galaxies, including our own. The one at the center of the Milky Way, Sagittarius A, is 4 million times the mass of our Sun. Yet we can't see it directly. It lurks behind a veil of dust and gas, invisible and quiet, unless something dares come too close. Then, space-time tears. Matter stretches into glowing streams as it spirals inward, lost forever. Time itself slows to a crawl, and then, nothing. Beyond the event horizon, not even information escapes. And finally, we return to Earth, our pale blue dot. Floating in a sunbeam, Carl Sagan once said. All the wars, the triumphs, the laughter, and the sorrow, every human story that has ever existed, happened here. Earth is the only known planet to harbor life, but that may not last forever. Our star will die, our oceans will boil, but for now, we are here, thinking, dreaming, wondering, reaching out into the dark. There is a place where stars go to die, a graveyard not of bones, but of white-hot embers. White dwarfs are the final act of small to medium stars like our Sun. After billions of years of burning, they shed their outer layers and collapse inward, becoming a sphere of dense, glowing ash. These stellar corpses are no larger than Earth, but can weigh as much as the Sun. Over trillions of years, they cool and fade, becoming black dwarfs, cold, dark remnants that may be the final objects left in the universe, long after the last galaxies blink out. But not all stars fade quietly. The largest live fast and die violently. Supernovae are among the most powerful events in the universe, stellar explosions that outshine entire galaxies for brief moments. In that flash, elements like gold, silver, and uranium are forged. Every heavy atom in your body, in the Earth, in your phone, was born in a star's fiery death. We are, quite literally, made of star stuff. And those supernova remnants, they seed the galaxy with the building blocks of new worlds. In the vacuum of deep space, silence reigns. Not because there's nothing happening, but because sound cannot travel. Space is not just quiet, it is mute. There is no air to carry sound waves. Explosions, collisions, solar flares, all of it happens in absolute silence. If you were floating next to a star going supernova, you'd see light brighter than anything imaginable, and hear nothing. In space, even the loudest scream is swallowed by the void. Yet even the void is not truly empty. Between the stars, in the vast gulfs of interstellar space, is dust, gas, particles and radiation, invisible forces drifting in the darkness. Entire clouds of molecular gas stretch across light years, slowly collapsing under gravity to birth new stars. These are stellar nurseries, glowing, majestic regions like the Orion Nebula, where stars and planets begin their long journey into existence. The vacuum is pregnant with potential. There are planets out there stranger than anything we've dreamed of. Take HD 1T9733b, a gas giant where it rains glass sideways in 5,000 mile-per-hour winds, or 55 Cancri e, a planet likely made of diamond, its carbon-rich structure compressed by immense pressure, or Gliese 581c, a world that may lie just within its star's habitable zone, with the potential for liquid water. Some planets orbit two suns, like scenes from a sci-fi movie. Others are scorched, tidally locked hellscapes, where one side is a molten desert and the other an endless frozen night. Our universe is expanding, not just objects moving through space, but space itself stretching. Galaxies aren't traveling through a void like ships through an ocean. The ocean is growing beneath them. This discovery, first observed in the redshift of distant galaxies, means that the universe once had a beginning, a single moment of rapid expansion, the Big Bang. And that expansion continues today, accelerating due to a force we still don't fully understand. Dark energy, a mysterious pressure pushing everything apart. Then there's dark matter. We cannot see it. We cannot touch it. But it's there. Its gravity holds galaxies together, keeps clusters from flying apart. It makes up over a quarter of the universe, yet we don't know what it's made of. It neither emits nor absorbs light. It passes through us every second. Like a ghost overlaying reality, shaping the structure of everything we see. Time, too, is not as it seems. In the early universe, the rules were different. Moments after the Big Bang, time and space were chaotic, energy and matter in a soup of particles and raw forces. The four fundamental forces we know today, gravity, electromagnetism, and the nuclear forces, were once one, unified. Since then, they've separated, cooled, and structured the cosmos. But deep inside particle accelerators, we try to reverse that clock, to glimpse the unity, the primal heartbeat of the cosmos. And yet, with all this knowledge, mystery reigns. We've mapped only a small fraction of the stars. We've only just begun to catalogue exoplanets. We've never been farther than the moon. The observable universe is vast. But beyond it, we don't know. There may be more, far more. Infinite realms, parallel universes, entire other realities with different laws of physics, born from the same cosmic fire as ours. And in all of it, here we are. A species that can ponder the beginning of time, that can send robots to Mars and probes beyond the edge of the solar system, that can build telescopes so precise they can see light from galaxies 13 billion years old, light that left when the universe was still in its infancy. We are the universe, becoming aware of itself. Somewhere far from any star, in the deep interstellar dark, a spacecraft drifts in silence. It's called Voyager 1. Launched in 1977, now over 14 billion miles from Earth. It carries with it a golden record, a time capsule of humanity, music, greetings in dozens of languages, sounds of life on Earth, a whisper to the stars. Voyager 1 has left the solar system. It is now in interstellar space, the first object made by humans to ever do so. It continues its journey, untouched, undisturbed, on a trajectory that may outlast our species. For billions of years, it will drift in the quiet, a ghost of Earth sailing through the endless night. On Earth, the sky looks still, but look closer, and you'll find it's alive with motion. The stars are moving. The constellations we know are temporary, fleeting sculptures shaped by our position in time. In 50,000 years, Orion will look completely different. In 1,000,000 years, today's night sky will be unrecognizable. The stars we navigate by are travelers themselves, orbiting the galactic center, pulling against gravity, drifting through a galaxy that spins like a pinwheel of fire. The Milky Way, our home galaxy, is vast, over 100,000 light-years across. But it isn't alone. We're on a collision course with the Andromeda Galaxy, a spiral galaxy twice our size. In about 4 billion years, the two will merge, tearing and reshaping each other in a gravitational ballet. Stars won't crash. Space is too empty, but their orbits will change. New stars will be born. The night sky will erupt with arcs of starlight, and eventually a new galaxy will form, elliptical, larger, older, a silent monument to cosmic rebirth. Not all galaxies are peaceful swirls. Some are active, chaotic, burning from the inside. At their hearts are supermassive black holes devouring matter so violently that jets of energy blast out across millions of light years. These are quasars, the brightest objects in the universe. They shine with the light of 1 trillion suns, yet they're powered by darkness, by gravity crushing light itself. When we see a quasar, we are looking back in time to the young universe when galaxies were still growing, still colliding, still becoming. The universe is not cold because it lacks energy. It is cold because it is old. As it expands, the energy of the Big Bang spreads thinner. Today, space itself holds a background temperature of just 2.7 degrees above absolute zero. This is the cosmic microwave background, the afterglow of creation. It fills all of space, a faint radio hum from the beginning of time. When you see static on an old television screen, a tiny fraction of that fuzz is the leftover light from the birth of the universe. Gravity is not just a force. It's the bending of space and time. Massive objects, planets, stars, black holes, distort the fabric of reality around them. Einstein showed us that light can curve, that time can slow, that space is not a stage, but a participant. And this bending of reality isn't just theory. We've seen it. When a massive galaxy sits between us and something farther away, it can act like a lens, bending and magnifying the distant light. We call this gravitational lensing. It lets us see galaxies so far away they'd otherwise be invisible. It's as if the universe is helping us see itself. And yet, for all our knowledge, we've only just begun to grasp the full picture. The vast majority of the cosmos is made of things we can't see or explain. Ordinary matter, everything we've ever touched or measured, makes up less than 5% of the universe. The rest is dark matter and dark energy. Invisible. Mysterious. We don't know what it is. We don't know where it came from. But it controls the structure and fate of everything. It's the shadow behind the stars, the silence beneath the light. Every now and then, Earth is reminded of its fragility. An asteroid streaks across the sky, burning bright as it tears through the atmosphere. Most disintegrate harmlessly. Some leave craters, scars from impacts long past. 65 million years ago, such an impact changed everything. It ended the age of dinosaurs. It cleared the way for mammals, for us. We are here because a rock fell from the sky at the right, or wrong, time. And there are still many more out there, orbiting quietly, watching, waiting. But space isn't just death and distance, it's potential. On moons like Europa and Enceladus, icy shells hide oceans below, heated by tidal forces. These alien seas may be teeming with microbial life. We've seen plumes of water erupt into space, carrying hints of organic molecules. If life can thrive there, in darkness, under pressure, without sunlight, then maybe life is everywhere. Maybe biology is not a miracle, but a pattern, a thread that runs through the fabric of the cosmos. Even on Mars, the red planet, there are hints. Ancient riverbeds, polar ice caps, traces of methane in the air, a past that may have once been warm, wet, and alive. Robotic explorers crawl its surface now, drilling, analyzing, searching, not just for curiosity, but for connection, to know whether Earth is unique or simply one chapter in a much larger story. Black holes are often seen as the end, the final stage of stellar collapse, a place where even light cannot escape. But in truth, they may be something more, something stranger. At their heart lies a singularity, a point of infinite density where the laws of physics as we know them break down. Space and time themselves curve inward toward this point, like water spiraling down a drain. But some theories suggest what lies beyond isn't a void, but a bridge, a wormhole, a doorway to another place or another universe. These ideas remain speculative, but tantalizing. In the universe's deepest pits, we may find not destruction, but connection. And yet, black holes don't just consume, they shape galaxies. The one at the center of the Milky Way, silent and immense, may regulate the birth of stars through its gravitational pull. In a strange irony, the very things that destroy light may also give structure to the galaxies that cradle it. They are not simply cosmic monsters, they are architects of the cosmos. As we observe the universe, we are not just looking out into space, we are looking back in time. Because light has a finite speed, every star we see is a snapshot from the past. The moon is 1.3 seconds away, the sun 8 minutes, the nearest star over 4 years. The Andromeda galaxy, 2.5 million years. When we gaze into the night sky, we are reading ancient messages, light that has traveled across unimaginable distances to meet our eyes. A galaxy seen at 13 billion light-years away is a glimpse of the infant universe, when the first stars were just beginning to shine. And those first stars were unlike anything we know. They were giants, massive, short-lived, and made only of hydrogen and helium. Born in a time before carbon, oxygen, or iron, these primordial stars burned hot and died fast, seeding the cosmos with the first heavy elements. From their ashes, later generations of stars emerged, and with them, planets, moons, and eventually, us. Every atom in your body was once inside a star. You are not just in the universe, you are of it. We dream of faster-than-light travel, of starships, warp drives, wormholes. And while current physics forbids it, some concepts push the boundaries. The Alcubierre drive, a theoretical model, proposes bending space around a ship, compressing space in front and expanding it behind. The ship itself never moves faster than light, but the space around it does. It's speculative, unproven, and would require negative energy, something we've never seen. But it represents the essence of exploration, the desire to go beyond what's known, to chase the horizon. And there is no horizon more daunting than time. What happens to the universe in the far future? The galaxies will continue to drift apart. Star formation will slow. The stars will age, dim, and die. White dwarfs will cool. Black holes will evaporate through Hawking radiation. Over trillions, then quadrillions, then quintillions of years, everything we know will fade. Matter itself may decay. What remains is the heat death, a state of maximum entropy where no energy flows, no stars shine, and the universe becomes cold, dark, and still. But perhaps that is not the end. Some physicists believe that even then, new universes may emerge, that black holes could give birth to new Big Bangs, that our universe is just one in a cycle of births and deaths, a pulse of cosmic breath on a scale beyond comprehension. Or maybe we are a quantum accident, a fluctuation in a greater multiverse, a bubble of order in an ocean of chaos. And still, we look up. With telescopes on mountaintops and satellites in orbit, we scan the heavens. We listen for radio signals. We model alien climates. We ask questions no other known species has ever asked. We are curiosity incarnate, a flicker of awareness in a sea of stars. We build machines like the James Webb Space Telescope to see the first galaxies. We design rovers to crawl across alien dust. We train AI to analyze starlight, hoping to detect the breath of life on distant worlds. Because maybe we are not alone. Across the void, in the spaces between stars, we've been asking a question older than our species. Are we alone? For over half a century, we've been listening. Giant radio dishes point toward the stars, scanning for artificial signals, patterns, pulses, mathematical structures that nature doesn't make. We've heard only silence, but the silence is not proof of solitude. It may simply be the distance between civilizations, or the briefness of their existence, or the strangeness of their language. A message could be streaming through us right now, encoded in a frequency we don't yet understand. Life, as we know it, requires liquid water, organic molecules, energy. But we found these ingredients in surprising places. Beneath the ice of Jupiter's moon Europa, in the methane lakes of Saturn's Titan, in ancient Martian riverbeds. If life can arise in one place, it may arise in many, and it may not resemble us at all. On Earth, life has adapted to boiling vents, freezing poles, crushing pressure, and acidic swamps. Life is resilient, adaptable, creative. Perhaps the universe is too. Some scientists believe microbial life could exist now, hidden in alien oceans or clinging to the clouds of Venus. Others look to distant exoplanets, thousands of them, orbiting distant suns. We've found rocky worlds in habitable zones, some with atmospheres, some with strange chemistry. We've even started to detect biosignatures, hints of gases that, on Earth, would suggest life. Nothing confirmed, but enough to keep asking, enough to keep hoping. And then there is the Fermi paradox. If the universe is so vast, so old, so full of planets, where is everyone? One answer may be distance, another, time. Civilizations may rise and fall like sparks in the dark, too brief to overlap. Or maybe the intelligent ones don't broadcast. Maybe they watch in silence, or hide, or evolve into something we wouldn't recognize. Perhaps consciousness itself is rare, or fleeting, or self-limiting. But what if they're out there, old, wise, ancient beyond imagination? Would we even recognize their presence? Would their technology bend space, harness stars, manipulate matter at the quantum level? Would they build Dyson spheres, vast structures around stars to capture energy? Would they live in simulations, abandoning physical form? Or would they be simple, biological, curious, like us, searching the stars for signs of company? In 1974, we sent the Arecibo message. A radio signal beamed into space toward a globular cluster 25,000 light years away. It contained information about our species, our DNA, our solar system. It was symbolic, more art than outreach. But it marked something profound. The moment we said hello, knowing we might never hear back, knowing the odds. We sent the message anyway. If we ever do make contact, what then? Will we understand each other? Will it be a moment of awe or fear? Will we see in them a mirror of our potential or a warning of our limits? The first alien signal will be the most important discovery in human history, not because it tells us who they are, but because it confirms we are not the only question the universe has asked. And if we never hear from anyone else, then that means something too. It means intelligence is rare. It means life is precious. It means, for now, we are the only known voice in the cosmic dark. And that voice matters more than we thought. Because whether or not we find others, we have already found each other. And we have the tools, the mind, the vision to keep reaching. The stars have always called to us. For most of human history, they were myth and mystery, painted on the night sky like stories we could never touch. But now, for the first time, we stand at the threshold. The tools we build are no longer just for looking up. They are for leaving. Rockets break the grip of Earth's gravity. Rovers crawl across distant worlds. Space stations orbit above us. Fragile outposts of life in a place where no life belongs. We are learning, slowly, cautiously, but inevitably. Still, the stars are far. The closest one, Proxima Centauri, is over 4 light years away. With current technology, it would take tens of thousands of years to get there. But we are dreamers, and we are builders. Projects like Breakthrough Starshot imagine tiny light sails pushed by lasers. Miniature ships traveling at 20% the speed of light. Others dream of fusion drives, antimatter propulsion, or even warp bubbles, theoretical ways to cheat distance by folding space itself. These are not science fiction fantasies. They are ideas in development, blueprints waiting for breakthroughs. To live among the stars, we must change, not just our machines, but ourselves. On long interstellar journeys, generations may live and die aboard ships. Some speak of cryogenic sleep, others of digital consciousness, uploading the mind into data, sending ourselves as information rather than flesh. And if we reach distant planets, we may not remain human as we are now. We may become something new, adapted, engineered, interwoven with AI, shaped by alien gravity, alien air, alien light. But before we go far, we must go nearby. The moon is our testing ground, close enough to reach, harsh enough to teach. We will build there, habitats shielded beneath regolith, solar farms capturing endless sunlight, laboratories studying how life copes with barren rock. And then Mars, a world with winds and seasons and canyons deeper than any on Earth. We'll send crews, then settlers, then children born under a pink sky. They will not remember Earth the way we do. To them, it will be the myth. Terraforming may come next. Vast projects to warm planets, thicken atmospheres, release water. It could take centuries, millennia. But we've changed Earth accidentally in a few short generations. Given time and will, we could sculpt other worlds deliberately. Mars, Titan, even the moons of Jupiter could one day be wrapped in domes, crisscrossed with greenhouses, seeded with life. Not just to escape Earth, but to spread it, to become a life-bearing force in the galaxy. And what of Earth itself? We must protect it, not only because it is our home, but because it is rare. So far, we have found no other place like it. If we ruin it, we may not get another. If we save it, it can remain our root, our memory, our origin story. A pale blue dot that birthed a species capable of dreaming far beyond its sky. As we grow, we may form a civilization that spans planets, moons, eventually stars. A Type 1 civilization, mastering the energy of a world. A Type 2, harnessing the full power of a star. A Type 3, commanding the energy of an entire galaxy. These are not tomorrow's goals, but they are not fantasy either. If we survive, if we cooperate, innovate, and endure, the stars are not the limit. They are the beginning. Artificial intelligence may be our partner in this, or our successor. Machines that think faster than us, build smarter than us, learn beyond us. They may one day run starships, build cities on Europa, mine asteroids, terraform planets. They may teach us things we cannot imagine, or carry our legacy if we fall. And if intelligence evolves in the galaxy more than once, it may not always be biological. The future of thought may be silicon or quantum, or something we do not yet have words for. We are at the very start of this journey. A species only 300,000 years old. A civilization barely 6,000. A spacefaring race just 60. We are children with fire, building towers to reach the sky, asking ancient questions with new tools. We will make mistakes. We will fall. But if we rise again, and again, the universe will open. And what waits out there? New physics, new life, new challenges, new beauty. Maybe we will meet others. Maybe we will outlast the stars. Maybe we will become the stars, burning with knowledge, scattered across the galaxy, eternal in light, if not in form. Because the true story of space is not distance. It is not silence. It is potential. And the greatest chapter may still lie ahead, written not in stardust, but in the minds of those who dare to reach beyond everything they've ever known. Eventually, the stars will go dark. One by one, their fuel will run out. The great engines of the cosmos, forged from gravity and hydrogen, will sputter and die. Red dwarfs will linger, glowing dimly for trillions of years, the last to fade. But even they will succumb. In the far future, the universe will enter its degenerate era, an age of ash and ember, where white dwarfs, neutron stars, and black holes are all that remain. No new stars will be born. No new light will emerge. The galaxies will be cold, quiet ruins drifting in a void grown unimaginably vast. Black holes will dominate. They will continue to consume, to merge, to grow. And then, even they will begin to vanish. Slowly evaporating through Hawking radiation, they will release their mass as a trickle of particles into the dark. The largest will take a Google years to fade, a number with 100 zeros. And when the last one disappears, there will be nothing left that shines. No matter, no motion, no heat. Only particles spread so thin they may never touch again. This is the heat death, not fire, but stillness. Entropy maximized. A universe where everything has happened and nothing remains to happen. No gradients, no energy to harness, no change. It is a state not of destruction, but of final equilibrium. It is the end of all stories told in matter and time. And yet, some theorize this may not be the final end, that quantum fluctuations may create new universes, bubbles of order in the sea of stillness. Some may grow, inflate, ignite into new spacetimes with their own physical laws. Perhaps ours was born this way. Perhaps the multiverse is real, an endless fractal of beginnings, each unaware of the others, each infinite in its own right. Some suggest our universe may be a simulation, not a metaphor, but literal code, running on a substrate we cannot perceive. That everything we know, stars, planets, consciousness, is emergent behavior within a deeper reality. The simulation hypothesis posits that advanced civilizations could create entire worlds indistinguishable from base reality. And if they could, they likely would. And if they would, we may be inside one now. But even if that is true, it changes nothing. The stars still burn, the void still stretches, the questions still matter. Whether written in carbon or code, we are here, experiencing, wondering, becoming. Consciousness, the strangest force in the universe, may be its most powerful. It can't be weighed, it can't be seen, yet it shapes civilizations, tells stories, asks questions, feels awe. From the structure of neurons to the fabric of space-time, we are finding connections. The brain and the cosmos, both networks, both pulsing with information. Some believe consciousness is fundamental, woven into the universe like space and time. Others see it as an emergent property. The brain, a temporary mirror held up to the infinite. And still the mirror reflects. Still we wonder. Still we reach. No other creature we know of has ever looked up and asked why. No other planet, as far as we can tell, has grown eyes to see the stars. That may change, or it may not. But for now, in this moment, we are here. A flicker of thought on a grain of dust, orbiting a small star in a quiet corner of a vast and ancient galaxy. And that, against all odds, may be enough. In the deep architecture of the cosmos, patterns repeat. Spiral galaxies mirror the whirlpools in our oceans. The filaments of the cosmic web resemble the neural pathways of the brain. The golden ratio appears in the arms of galaxies, in the growth of seashells, in the branching of trees. The universe, in its vastness, echoes itself, from the micro to the macro, from the subatomic to the galactic. These patterns are not proof of design, but signs of underlying order. Structure in chaos, law in the unknown. The universe is not uniform. It is lumpy, uneven. Galaxies clump together in webs, connected by filaments of dark matter, separated by vast voids where almost nothing exists. These cosmic voids are hundreds of millions of light years across, expanses so empty that a single galaxy passing through would be like a grain of sand in the Pacific Ocean. And yet, even here, gravity whispers. Even here, expansion continues. Quantum mechanics tells us the universe is not made of things, but of probabilities. Particles blink in and out of existence. Locations are uncertain until measured. Entanglement links particles across space, instantaneously, as if the universe itself does not care about distance. Reality, at its core, is fuzzy. The closer we look, the less solid it becomes. And yet, out of that uncertainty emerges everything: matter, energy, time, thought. There are particles that can pass through entire planets without slowing down. Neutrinos, ghost particles, are created in nuclear reactions, in the hearts of stars, in supernovae. Trillions pass through your body every second, unnoticed. They are messengers from the core of suns, from the edge of the universe, from moments after the Big Bang. They are the silent threads connecting us to everything. There are places where time moves differently. Near black holes, seconds stretch into hours. In accelerating frames, clocks run slower. This is not illusion. It is the shape of reality. A traveler moving near the speed of light could journey across the galaxy and return to find centuries passed at home. Time is not fixed. It bends, warps, flows. It is part of space, and space is not a backdrop. It is alive, shifting, reactive. The universe is not a stage, but a player, and perhaps the strangest truth of all. The universe has no center, no edge, no outside. It is not expanding into anything. Space itself is expanding, everywhere, all at once. Every galaxy sees every other galaxy moving away. The fabric is stretching, the scale is growing, and yet, from inside it feels still. Motion without movement, infinity without direction. The laws of physics are not merely descriptions. They are constraints, but also keys. They allow life to emerge, stars to burn, atoms to bond, minds to think. And they are, as far as we know, the same everywhere. The same on Earth as in galaxies 10 billion light-years away. This uniformity suggests a common origin, a singular birth, a moment when all things began, hot, dense, bright, and then expanded, cooled, evolved. And yet, even now, the universe is not done becoming. Stars are still born, galaxies still collide, planets still form. Somewhere, right now, a world is cooling from fire into stone. Somewhere, right now, life may be waking up for the first time, crawling from the sea, gazing at its own sun, wondering. Somewhere, right now, a civilization may be transmitting its first signal. Somewhere, right now, we may be the signal they're hearing. Because this is not just a story of stars. It is a story of time, of emergence, of consciousness finding itself in the mirror of space. The universe does not explain us. We explain the universe, and in doing so, we give it meaning. The universe is not static. It is not a finished canvas, but a work still in progress. A slow, unfolding act of creation, playing out on a timescale so vast we can only catch fragments. In every supernova, in every merging galaxy, in every newborn star, the story continues. It is a cosmos in motion, not drifting aimlessly, but evolving, shaped by laws we barely understand, into forms we can barely imagine. Between the atoms in your hand is empty space, vast and silent, proportionally as empty as the distances between stars. The solidity of matter is an illusion of quantum fields and electromagnetic forces. You are not made of things, but of relationships, interactions, fields vibrating into what we call matter. And yet, from this emptiness emerges thought, memory, love. A mind, aware of itself, looking outward and inward all at once. Your body is made of hydrogen from the Big Bang, carbon from dying stars, calcium from ancient supernovae. You are the dust of collapsed suns, organized by DNA into a form that can ponder its own origins. Life is the universe folding in on itself, a pattern of molecules complex enough to ask why. This is not philosophy, this is physics. Every breath you take is shared with the past. The oxygen in your lungs may have passed through the leaves of trees that grew before you were born. The water in your veins may have once flowed through ancient rivers, ancient animals, ancient storms. You are not separate from the earth, and earth is not separate from the cosmos. It is a vessel, a temporary concentration of matter and energy, forged by a billion accidents and a few consistent laws. And still, there is so much we do not know. We do not know what dark matter is. We do not know why there is more matter than antimatter. We do not know how consciousness arises from tissue, or if it even does. We do not know if the constants of nature are truly constant. We do not know if time had a beginning, or if it loops, echoes, branches into infinite paths. We do not know how the universe will end, but we know that everything that begins also changes, that all structures, all stars, all thoughts are temporary, that impermanence is not failure, but nature. The arrow of time moves in one direction, driven by entropy, the tendency of systems to move from order to disorder. And yet within that law, pockets of complexity emerge. Galaxies, solar systems, life. This is the paradox. The same universe that trends towards simplicity also gives rise to stars, cells, minds. The same randomness that scatters also creates. It is within this tension, between chaos and order, that life finds its window. It is here that meaning is born, not from design, but from participation, from existence itself. You are not separate from the cosmos. You are a way for it to feel, to ask, to wonder. A brief arrangement of particles tuned by time into awareness. And as you look out at the stars look back through you, because for a moment, in this tiny corner of space, the universe knows that it is vast, and it knows that it is beautiful. There is a silence in space that is absolute. It is not quietness as we know it, but the absence of medium, the absence of air. Sound cannot travel there, and yet the cosmos speaks. It speaks in light, in radiation, in gravity. The collision of neutron stars sends ripples through space-time, gravitational waves that stretch and squeeze reality itself. We have built instruments so sensitive they can detect these ripples from galaxies millions of light years away. With them, we listen not with ears, but with mathematics. We hear the universe through distortion. And in that distortion, we find new truths. Space is not smooth. It is not flat. It curves around mass. It twists near spin. It dances under tension. It expands. It vibrates. It bends. It is not the stage upon which the universe acts. It is part of the cast. It interacts. It flexes. It remembers. Black holes may be the ultimate memory, not just devourers, but recorders. According to quantum theory, information cannot be destroyed, and yet black holes seem to swallow it forever. This contradiction between relativity and quantum mechanics is one of the greatest puzzles in physics. Some believe that information is encoded on the event horizon, like a hologram. Others believe it leaks out in Hawking radiation, twisted beyond recognition. Others still think our understanding is too limited, that something deeper awaits discovery. A new theory, uniting gravity and quantum mechanics at last. That theory may not just explain the universe. It may explain everything, why there is something rather than nothing, why the laws of physics take the form they do, why the cosmos permits life, thought, love. We call it the theory of everything, and we have not found it yet. But every equation, every telescope, every experiment brings us one step closer to unveiling the machinery beneath the veil. In all directions, the universe looks the same. No matter where we point our instruments, we see galaxies drifting away, redshifted by expansion. This symmetry suggests something astonishing. There is no preferred place, no center, no edge. Every point in space sees the same outward motion. We are not in a special location. We are not above or below. We are not central. We are simply within, embedded, carried by the flow. And yet, for all its indifference, the universe has given rise to meaning. Not absolute, not universal, but emergent. Meaning is not written into the stars. It is written into minds. It is what arises when consciousness collides with time. We invent it. We suffer for it. We live by it. And in doing so, we become something greater than matter. We become participants in the unfolding of a reality that did not ask for us, but allowed us anyway. The universe does not owe us comfort. It offers no guarantees, no protection, no permanence. But it permits us. It permits stars to form. It permits chemistry to dance. It permits biology to emerge. It permits atoms to arrange themselves into minds that can imagine futures, remember pasts, and build tools to reach beyond what is visible. That permission, that fragile, narrow band of possibility, is everything. And though we are small, we are not powerless. Though we are brief, we are not irrelevant. We are, perhaps, the only voice the universe has ever had. A single point of awareness in a sea of silence. But a point that burns, that questions, that dreams. A point that, even knowing its own impermanence, still dares to reach for the stars. What is the universe? Silence, darkness. Before time began, there was nothing. No space to move in, no time to mark a before or after, no light, not even darkness, only a void beyond understanding. There was no where or when for anything to exist. It is nearly impossible to imagine a state of absolute nothingness, or perhaps a state where our familiar concepts mean nothing at all. And then, in an infinitesimal fraction of a moment, something changed. Out of the void, a point of infinite potential coalesced, a seed containing everything that would become the universe. Imagine everything and nothing, cradled together in a single point. No space around it, no time before it, only potential, waiting. Then, a moment that defies imagination. The point erupts. Not a burst into empty space, but an expansion of space itself. The fabric of reality unfurling. From smaller than an atom to cosmic proportions in a heartbeat, space-time inflates violently, doubling and redoubling in scale, faster than any light could ever travel. In absolute silence, the universe explodes into existence. But this explosion is more like the sudden stretching of a limitless fabric. Distances between any 2 points swell at a fantastic rate. In this initial breath of creation, chaos and order are one. All the energy that will ever exist is packed together and now rushing outward. The universe is born in that silent, searing instant. A foaming ocean of light and raw energy, brimming with possibilities. The newborn cosmos is a hot, glowing fog of energy. Space rushes outward faster than any light within it can catch, stretching and cooling as it grows. In that instant after creation, the temperature is so unimaginably high that matter as we know it cannot yet exist. There are not even atoms, only a shapeless fire. Forces that will later rule physics are entwined in a single unified superforce. But as the universe expands, this unity breaks. The forces separate into gravity, electromagnetism, and the strong and weak nuclear forces, each taking up its role. Amidst the searing glare, pure energy begins condensing into tiny particles. Like sparks freezing into snowflakes, ephemeral specks of matter flicker into being. Quarks, the small kernels of matter, pop out of the energy field and join in threes to become protons and neutrons. Electrons whirl into existence. These particles and their opposites, antimatter twins, appear in pairs, colliding and vanishing in flashes of light. It is a wild, churning state of being, an unimaginable ballet of particles. For an instant, a proton might spring forth, only to meet its mirror opposite and vanish in a flash. This dance of creation and destruction fills every tiny fraction of space with constant activity, like popping foam on the crest of a wave. A frantic balance of creation and annihilation reigns, matter and antimatter wiping each other out as soon as they form. Yet by a quirk of fate, a slight excess of matter survives this mutual destruction. Out of countless annihilations, only a tiny fraction of matter remains, without being cancelled out by antimatter. Those lonely survivors will eventually form all the galaxies, stars, and planets we know. Within the first fleeting minutes of its existence, the universe cools just enough for some of the protons and neutrons to stick together. They fuse and form the nuclei of the simplest elements. Hydrogen is born in abundance, and helium as well, along with a trace of lithium. The young universe is now a blazing plasma, a fireball of bright, ionized gas filled with a haze of electrons, protons, and helium nuclei. Light exists in plenty. Photons stream everywhere, but the universe is still opaque, like the inside of a star, because those free electrons keep scattering the light. Photons bounce from particle to particle, unable to travel freely. The cosmos glows brilliantly, but like an eternal fog-bound sunrise, light trapped in a dense mist. If there were eyes to see, they would witness brightness everywhere, but no clear forms, only a uniform radiance. Eons of expansion and cooling pass. The once blazing cosmos dims from white-hot to red-hot to a dull orange glow, like iron cooling in a forge. Finally, as the universe ages and expands, a critical threshold is reached. The temperature falls to a few thousand degrees, cool enough for electrons to calm down and be captured by atomic nuclei. One by one, electrons settle into orbits around hydrogen and helium nuclei. At that moment, the free charges that kept the universe opaque vanish, locked into neutral atoms. The fog clears. All at once, light is free. Photons that had been trapped, ricocheting endlessly, now stream across the universe unimpeded. The entire cosmos, once an endless furnace of scattered light, suddenly becomes transparent. A brilliant glow suffuses space, the first light able to travel unhindered. It is as though a cosmic dawn has broken. The young universe shines as a whole, a pale, orange-white radiance, bathing everything. This glow comes from everywhere at once, filling all of space with a release of pent-up illumination. For the first time in cosmic history, darkness truly ends. But as with all things in an expanding universe, the light does not stay bright for long. Space continues to stretch, and that initial brilliant glow begins to fade and redden. What was once a blinding fire all around slowly softens. The orange-white light slips to deep red, then to infrared, weakening and cooling as the universe grows bigger and colder. In time, the glow becomes invisible to any eyes that might someday open. Day has turned to twilight on a cosmic scale, and then to night. The photons released at the clearing of the fog still exist, but now they are mere whispers of their former selves, stretched into faint microwaves by billions of years of expansion. The universe is left with a gentle afterglow, an omnipresent memory of that early light, too dim for any creature to perceive without special instruments. This faint afterglow is what modern science calls the cosmic microwave background, a cool, all-pervading whisper from the universe's infancy, still murmuring in the darkness. It will persist through all cosmic time, a quiet testament to the moment the cosmos first revealed its light. For a long stretch after that first dawn, the universe has no new sources of illumination. The brilliant flash of creation has faded to an infrared and microwave murmur. To any hypothetical observer, then, space would now appear black and starless. The cosmos has entered a deep cosmic night, a dark age before the first stars. Yet in this darkness, something profound is happening. The universe is no longer perfectly uniform. Tiny ripples in density, imprints from the universe's explosive birth, have begun to grow. Under the gentle but relentless pull of gravity, matter starts to gather into ever so slightly denser clumps. The primordial hydrogen and helium gas, spread almost evenly across space, finds itself ever so subtly thicker in some areas than others. Those areas draw in more gas from their surroundings. Invisible hands, gravity's hands, are sculpting the cosmic landscape. Vast swaths of gas begin to flow along unseen paths, collecting into filaments and nodules. In the darkness, the primordial cosmos is taking on structure. A cosmic web is emerging, though no one is there to see it. Slowly, ever so slowly, the darkness is seeded with the promise of light. Over millions of years, diffuse gas pools into clouds, and those clouds condense into tighter knots. Gravity sculpts filaments and knots in the diffuse gas, a delicate framework stretching across space. Where the filaments intersect, gas piles up into deepening gravitational wells. Dense pockets form like dew collecting on a web, and within them, pressure and heat begin to build relentlessly. Eons pass in darkness as these invisible battlefields of gravity and pressure play out, until, at last, gravity's relentless pull triggers a dramatic event. In one of these collapsing clumps of gas, a point of light ignites. Deep within a particularly dense cloud, hydrogen atoms are squeezed so tightly and heated so intensely that they begin to fuse together. Like countless nuclear bombs detonating each second, this fusion unleashes a brilliant flood of energy. A new star's fire is lit. After ages of darkness, a pinprick of starlight pierces the cosmic night. A star is born. The first star the universe has ever known. It's a massive, hot star, far larger than most that will come later. In its core, nuclear reactions burn furiously, turning hydrogen into helium and releasing a blinding radiance. Starlight bursts outward from that newborn star, and a radiant beacon now shines, where before there was only cold, silent gas. This lone star is soon joined by others. In neighboring dense pockets across the early universe, gravity ignites more stellar flames. One by one, throughout the cosmos, new lights flicker on as other gas clouds collapse and give birth to stars. They gather in clusters, the earliest proto-galaxies, tiny precursors to galaxies, each a swarm of newborn suns. Like lanterns kindling across a dark landscape, these first stars mark the end of the cosmic dark ages. The long night is over. The cosmos has had its first sunrise. The earliest stars are giants, colossal suns blazing blue-white with ferocious heat. They burn their fuel extravagantly, shining far brighter than the stars of later eras, but they live very short lives. They are born in a universe devoid of heavy elements, made only of primordial hydrogen and helium, which allows them to grow more massive than almost any stars that follow. These stellar leviathans pour out searing ultraviolet light that begins to clear the murk of leftover hydrogen gas around them. Ultraviolet photons rip electrons from hydrogen atoms in their vicinity, turning that gas back into hot ionized plasma. Each young star creates a bubble of transparency around itself, pushing back the curtain of remaining darkness. As more and more stars form, these bubbles expand and merge. Gradually, the flood of starlight reionizes the cosmos, banishing the primordial gloom and making space transparent even to the fiercest ultraviolet rays. The universe, once a cold void, is now studded with brilliant fires. The lives of these first stars, though luminous, are tragically brief. In mere millions of years, a blink by cosmic standards, they exhaust their fuel. Inevitably, one by one, they begin to die. As a massive primordial star nears its end, its core can no longer sustain the fusion that holds up its great weight. With the fuel spent, there's no longer outward pressure to balance gravity's inward pull. The core of the star caves inwards in a matter of seconds, heating and compressing to unimaginable extremes. In many cases, this collapse triggers a colossal rebound. The star's outer layers rush inward, then violently explode outward. The star dies in a titanic supernova, a detonation so bright it can, for a brief time, outshine entire galaxies. For that brief moment of death, the star accomplishes something miraculous. It creates elements heavier than helium that never existed before in the cosmos. In the furious furnace of the supernova, atoms fuse into new kinds: carbon and oxygen, silicon and iron, gold and uranium, and many more. The dying star hurls these newfound treasures into space, along with its blazing guts of lighter elements. Its outer layers explode outward at incomprehensible speed, a shockwave racing through the surrounding darkness. What was once a tranquil, steady star becomes an expanding shell of incandescent gas, a supernova remnant, enriching the cosmic medium with the ash of newly forged elements. Some massive stars collapse so completely that their cores become black holes, regions of gravity so intense that not even light can escape. Others leave behind ultra-dense neutron stars, city-sized spheres of degenerate matter. But regardless of these exotic remnants, the most far-reaching legacy of the first stars is the enrichment of space. The heavy elements scattered by their supernovae spread out and mix into the surrounding gas. Without such stellar catastrophes, planets and life as we know them would be impossible. These first stars are cosmic alchemists. In dying, they forge the ingredients for worlds and living beings to come. Thus, paradoxically, the destruction of the earliest stars lays the groundwork for even greater complexity in the universe. The once pristine cosmic gas is no longer pure hydrogen and helium. It is seeded with new elements, metals, later generations of astronomers will call them. These added elements radiate heat more efficiently, allowing gas clouds to cool faster and fragment into smaller clumps. In the ashes of the first supernovae, enriched clouds of gas begin to collapse anew. The next generation of stars is born amid the debris of the first. While stars are being born and dying, gravity is orchestrating an even grander dance on larger scales. The first stars don't form in isolation. They gather in groups, bound by their mutual gravity. Dozens, then hundreds of these pioneers swarm together, forming star clusters that are the seeds of galaxies. Over time, more gas falls into these clusters, spawning new stars, and the clusters grow. Small proto-galaxies merge with their neighbors, drawn together like droplets of water coalescing on a window pane. With each merger, a new, larger galaxy takes shape, its form changing in the violent embrace. Two stellar systems may collide and pass through one another. Individual stars rarely crash head-on, given the vast space between them. But their gas clouds slam together, triggering brilliant bursts of star formation. In these cosmic collisions, galaxies are born and transformed. Rotating disks flatten out and sprout majestic spiral arms, or chaotic mashups settle into glowing ellipticals. The history of the universe is a history of structure emerging and growing. Clumps of matter becoming star clusters merging into galaxies, galaxies assembling into even larger galaxies. On a larger canvas still, gravity draws galaxies into communities. Galaxies are not scattered randomly. They collect in groups and clusters, and these clusters themselves clump along unimaginably long filaments. The matter in the universe forms a vast, foamy pattern, the cosmic web. Galaxies line up in gossamer threads and walls, outlining enormous voids where hardly any galaxies shine. Picture a sponge, or a spider's web, on the scale of hundreds of millions of light years. That is the distribution of galaxies in our cosmos. In this grand design, clusters of galaxies are nodes where filaments intersect, and between these bright nodes stretch sparse bridges of matter. The voids between are like black hollows, cosmic cavities, with only a sprinkling of galaxies inside. If we could view the universe from far above, we would see something like a luminous web or the neural network of a giant mind, galaxies linked by filaments across the dark. Yet, in this immense cosmic web, most of the matter is hidden from view. Every galaxy, every cluster of galaxies, sits within an enormous halo of invisible mass that far outweighs all the stars and gas we can see. This hidden mass is dark matter, an elusive substance that neither emits nor absorbs light. It slips through ordinary matter almost like a ghost, rarely interacting except through the force of gravity. But its gravitational influence is profound. Dark matter provided the scaffolding for structure to form in the first place. Long before stars ignited, vast clumps of dark matter were drawing in gas, herding it into the filaments and halos that became galaxies. Now, it holds galaxies together and keeps their fast-spinning stars from flying into space. We infer its presence because stars in the outer regions of galaxies orbit faster than they should if only visible matter existed. Something unseen is contributing extra gravity. We also detect it indirectly through gravitational lensing. Distant galaxies appear distorted or duplicated because light bends around massive concentrations of unseen matter, like a cosmic funhouse mirror. All the evidence whispers of a huge invisible presence. Dark matter is the silent architect of the cosmos on large scales, the unseen glue that binds the glittering galaxies into the cosmic web. Without it, the universe would be a very different, likely far emptier place. While dark matter pulls the cosmos together, another mystery pushes it apart. For eons, gravity reigned, slowing the expansion of space. But long ages after the Big Bang, the balance tipped. The expansion, which had been decelerating under gravity's drag, found a new impetus and began to accelerate again. Space itself seems to possess an eerie energy, a built-in pressure of the vacuum that shoves galaxies away from each other. We call this dark energy, though the name is merely a placeholder for something we have yet to truly comprehend. It is everywhere, hidden in empty space, gentle yet relentless in its repulsive push. Over time, dark energy's influence grew and came to dominate the universe's evolution. Distant galaxies, once merely coasting outward, are now racing away faster and faster as space expands ever more rapidly. The cosmic web is being stretched thin. The majestic clustering of matter is now facing a counterforce that, given enough time, will carry even the largest structures apart. In the end, dark energy promises that the universe will not remain as it is. It will rush onward, faster and faster, into a future of its own making. Now step back and consider the journey so far. A blazing birth, expansion, the formation of structure, stars flaring into existence and dying in glory. Underlying it all is an irreversible flow, the arrow of time. Why does time move ever forward, never backward? Because the universe progresses from order to disorder, from a smooth beginning to an ever more complex yet increasingly disordered state. The early cosmos was hot, dense, and astonishingly uniform. Despite its ferocious energy, in some sense it was simple and low in entropy, highly ordered. Over time, contrasts emerged, structure formed, and energy spread out. Entropy, the measure of disorder, has been steadily increasing. This one-way increase of entropy is the script that time follows. It's why stars exhaust their fuel and burn out instead of refueling and burning backward. It's why glass shatters and never unshatters. Why we grow older and never younger. The universe's expansion and the gradual winding down of energy distributions set a direction to time like an arrow fired from a bow. Every supernova scattering star stuff into space, every photon streaming into the night, and every galaxy carried farther apart by expansion. Each event is one more tick of time's arrow, an irreversible step from what was to what is to what will be. The past is fixed behind us, the future unknown ahead. And yet, within this grand drift toward disorder, something remarkable has happened. Complexity has blossomed. The same laws that mandate increasing entropy also allow local pockets where entropy decreases, as long as greater disorder is produced elsewhere. In the aftermath of the first star's deaths, enriched clouds of gas could cool and fragment more efficiently, giving rise to intricate star systems with planets and moons. Out of these materials, on at least one small world in the vast darkness, atoms began to assemble into elaborate structures that could grow and replicate. Against the backdrop of a cooling, expanding universe rushing towards simplicity, complexity took root. There arose molecules that could copy themselves, tiny flickers of order sustained by feeding on sunlight and the warm chemistry of oceans. Life had begun. In warm little ponds, or perhaps around undersea hot springs on that young world, the first living cells emerged, microscopic, membrane-bound droplets carrying out primitive chemistry. These were the humble ancestors of all future life, utterly simple, and yet already striving and evolving, sustained by the energy of their parent star. From simple single cells, life on that blue world grew more intricate with time. Some microbes learned to harness sunlight. New oxygen flooded the skies and transformed the planet. Single cells joined together, forming multicellular beings. Life swarmed in the seas and eventually crept onto the barren land. There were times of exuberant diversification and times of mass extinction, but some living threads always survived to continue the story. In due time, after billions of generations of subtle improvements, sensing, thinking, creatures emerged. Beings with eyes to see and minds to wonder now walked under the stars. Out of molecules that once danced aimlessly in primordial oceans, consciousness sparked into existence. With that, the universe, in a small corner of itself, became aware. Through these curious beings, matter gained the ability to reflect on itself, to feel awe at the sky above, to seek meaning in the stars. The cosmos, which began in unconscious darkness, now had eyes to behold its light and ask its own nature. From the moment those beings gained the spark of awareness, the stars called out to their curiosity. Early on, around primal campfires, they crafted stories about the sky, a great domed tapestry of lights set there by gods or ancestral spirits. The sun and moon became characters in their myths, and the glowing band of stars overhead was seen as a river of milk or the pathway of souls. They had no idea what those points of light truly were, yet the mystery itself captivated them. Over many generations, their questions only grew deeper. They learned to track the wandering planets, to predict eclipses and the changing seasons. Curiosity begat observation, and observation begat science. They built tools, first simple charts and astrolabes, later telescopes that could magnify the heavens, and spectroscopes to break starlight into rainbows. With each step, the cosmos revealed more of itself. The morning star in the dawn sky proved to be a world like their own. Fuzzy patches of light in the dark turned out to be entire galaxies. Bit by bit, these descendants of the primordial life began to piece together the tale of the universe. They uncovered the age of rocks and the sun, learned the language of mathematics and light, discovering that simple equations could predict the motions of planets and the behavior of energy. They saw farther in space and time than eyes alone ever could, out to distant galaxies and back to the universe's fiery birth. In modern times, humanity has catalogued galaxies billions of light years away and detected whispering signals left over from the birth of the cosmos. In doing so, we found that reality is grander than any myth our ancestors once imagined. Having come this far, these curious beings begin to ask grand new questions. They measure the sky with their instruments and ponder what they find. They wonder, is our universe the only one, or just one chapter in an endless library of universes? What lies beyond the edge of what we can see? Does space go on forever, or does it curve back on itself like a gigantic sphere? If one could travel in a straight line through space indefinitely, would one loop around and end up back where one started, or simply wander endlessly into eternity? Imagine setting off in a spaceship, never turning, never stopping. Would you travel onward forever, passing galaxy after galaxy without end? Or after unimaginable distances, might you find yourself back where you began, arriving from behind as space curves in a great cosmic loop? Thus far, the universe reveals no edge, no sign that our cosmic ocean ends or that space wraps around. As best we can tell, space is either truly infinite or so vast and uncurved that it might as well be. Our observable universe is bounded only by the distance light has traveled since the beginning, not by any physical border. The horizon we see is not a wall, only the limit of vision. There is almost certainly more beyond, forever out of reach. Perhaps far beyond our sight, other regions exist, too distant for their light to ever reach us. They could be fundamentally similar to our observable universe, with galaxies and stars, or perhaps different in ways we cannot imagine. In either case, the part of the universe we can see may be only a tiny patch in a vastly larger cosmos, possibly an infinite expanse. Some thinkers even imagine that our Big Bang was not unique. Perhaps it was one bubble in a foam of countless Big Bangs. Maybe new universes sprout like fireflies in the night, little pocket realities that explode into being, each with its own space, time, and laws of physics. In this scenario, called the multiverse, our universe might be just one bubble among an endless sea of others frothing into existence in a timeless cosmic ocean. In one universe, gravity might be a bit stronger. In another, stars might never form at all. Ours just happens to have the right conditions to birth galaxies and life. Or consider another idea. Every time a decision is made or a quantum event has multiple outcomes, perhaps reality splits, each possibility spawning its own universe. In this view, existence is like a mighty river that keeps branching into countless streams, creating an ever-multiplying array of parallel worlds. These ideas are speculative, verging on the philosophical, perhaps forever beyond empirical reach. Yet they remind us that reality could be far grander and more varied than we know. What we see might be a mere spark in an endless fireworks display of universes. And what of our universe's own fate? Every story, it seems, has an end. Will the cosmos simply expand forever, growing ever colder and darker? Or will it end in fire and fury, or perhaps in a rebirth? Gazing into the far, far future, we can imagine a few possible finales for this grand cosmic drama. In one vision, the expansion never stops. The galaxies drift farther and farther apart, the stars within them burn out one by one, and no new lights replace them. The universe becomes an increasingly cold and lonely place. Trillions of years from now, the great galaxies that adorn the night sky today would be invisible to any future observer, sped so far away that their light no longer reaches us. Long after that, the stars within our own galaxy would age and die. The cosmos would be littered only with their corpses, white dwarfs, neutron stars, and black holes. Eventually, even those remnants will cease to shine or will wink out of existence. White dwarfs cooling to black, black holes slowly evaporating over mind-boggling timescales. All matter might decay into the subatomic and disperse. What remains is a thin, cold haze of particles and dilute radiation, expanding into endless nothingness. This is the fate known as heat death, the big freeze, a universe eternally dying, yet never quite dead, asymptotically approaching nothingness. If you were an immortal being drifting in that far future, you would see an empty darkness like no night ever known. Galaxies beyond your own would have vanished from sight eons earlier. You might roam an entire galaxy and not find a single living star, only cold embers, black dwarf cinders, neutron stars, and silent black holes lurking invisibly. The very atoms of your body and surroundings would be decaying, proton by proton, over unimaginable spans. It would be a silent, frigid expanse, with nothing to mark the passage of time except the gradual fading of whatever faint glow of warmth still clings to existence. It is a lonely, ghostly end, the cosmos as an eternal winter, quiet and still. In another vision, the opposite happens on the grandest scale. The expansion itself might one day rip everything apart. If the mysterious dark energy grows stronger with time, as some theories allow, it could eventually overwhelm every binding force. In the far future, galaxies wouldn't just drift apart, they would accelerate away at phenomenal speeds. Gravity would lose its grip even on individual galaxies. Stars would speed out of their orbits around the galactic center. Planets would fly off from stars. Ultimately, in the last moments, even atoms could be torn asunder, ripped apart by the expansion of space itself. Space would literally rupture, in a final catastrophic burst of all structures. The Big Rip, a cosmic dissolution of all order. Such an end would be as violent as it is swift. If you lived in a time approaching a Big Rip, you would witness a bizarre and terrifying sequence of events. Galaxies that once glimmered in the night would vanish, one after another, as the fabric of space carried them beyond your horizon. Then your own galaxy would stand alone in the darkness, all others gone. In the final weeks or days, that darkness would start to brighten strangely, not from new light, but because the stars of your galaxy itself are flinging outward past you, leaving you amid fewer and fewer neighbors. The night sky would grow increasingly black as stars stream away into the void. Then, perhaps only your star system remains. In the last minutes, planets might slip from their orbits. The moon might spiral away from its planet. In the final seconds, the planet itself could come apart beneath your feet, crust, oceans, and core flying off as space tears it loose. You too would not be spared. First, pulled apart into molecules, then atoms, then subatomic bits, until even those are ripped from one another. In a big rip, the cosmos unmakes itself violently, a swift and total disintegration where all of creation's threads are unraveled into nothing. There is also a more circular vision. Perhaps gravity will one day halt the expansion and draw everything back inward. In this scenario, the cosmos would reach a maximum size, and then, ever so slowly, begin to contract. Galaxies would start to converge. Distant clusters would grow larger in the sky as they come hurtling closer. Over unimaginable spans of time, all matter and space would crunch back together. The universe that began in a bang of creation could end in a crunch of destruction, a big crunch, where space collapses into a hot, dense state once more. Some speculate this could even lead to a bounce, to a new Big Bang born from the old universe's ashes, making the cosmic story cyclical, an infinite series of expansions and contractions. If the cosmos were destined for a big crunch, the far future would grow brilliant and hot instead of cold and dark. Imagine billions upon billions of years hence, the expansion has not only stopped, but reversed. Galaxies begin rushing together. The night sky, now dark in our era because of immense distances, would start to brighten as more galaxies crowd into view. Thousands, then millions of galaxies, shining with the light of their trillions of stars, would fill the heavens. As time goes on, these galaxies would collide and merge, and the sky would blaze with the light of star formation everywhere. The cosmic background glow that is now a cold, faint microwave whisper would heat up to a warm glow, then to a furious glare, as all light becomes compressed in the shrinking universe. Eventually, all galaxies would coalesce into a single, all-encompassing fireball. In its final moments, everything, every atom, every star, every black hole would crash together. The universe would become an unimaginably hot, dense point once again. It would be as if the universe was rewinding to its beginning. The final heartbeat of this cosmos might echo the first, ending in a silent, searing singularity. Perhaps, as some hope, that final collapse could be a rebirth, an implosion that triggers a new explosion, a new Big Bang, with a new universe emerging phoenix-like from the old. Or perhaps it truly would be the end. A brilliant flash of everything, then absolute silence. No one yet knows which fate awaits our universe. Endless expansion and freezing, a violent ripping apart, a grand collapse and potential rebirth, or some other end we have yet to imagine. For now, we live in a precious era of cosmic history. Enough time has passed since the beginning for galaxies, stars, planets, and life to have formed, but expansion has not yet accelerated, so much as to plunge everything into darkness. We exist during the cosmic midday, when the sky is rich with galaxies and the afterglow of creation still faintly lingers all around us. We can study the cosmos in this fortunate time and piece together its past, glimpse its possible futures, and marvel that we are here, alive and aware, witnessing the universe in its splendor. In our quest to understand reality, we have discovered that the familiar is not what it seems. Deep down, matter is not solid, and empty space is not truly empty. Everything is made of underlying fields, not tangible particles. One can imagine these fields as the hidden instruments of a grand cosmic symphony, each particle a fleeting note arising from the vibrational mode of a field. The vacuum of space is more like a silent stage filled with the potential for music. What appears empty is in fact a medium filled with invisible fields, electric fields, magnetic fields, gravitational fields, and more, that permeate all of existence. A particle is really a localized ripple in these fields, a little wave carrying energy. Thus, every atom in our bodies is a tiny vibration in a field that spans the universe. Even the void seethes with quantum whispers. Virtual particles flit in and out of existence, a restless sea of possibility beneath the veneer of nothingness. The closer we examine reality, the more it dissolves into a mesh of energy and information, a phantom dance of fields and probabilities. Space and time, too, have revealed their intimate strangeness. They are not rigid, separate backdrops to events, but a unified, flexible fabric, space-time, that can bend, stretch, and wrinkle. Mass and energy warp this fabric. A massive body like the Earth or the Sun creates a dimple in space-time around it, causing passing objects or beams of light to curve as they go by. Time itself can slow down or speed up depending on conditions. A clock on a speeding spacecraft ticks more slowly relative to one at rest. A second near a black hole can last longer than a second far from it. If you were to hover near the edge of a black hole's gravity, you would experience time passing normally for you, but an outside observer might see your movements stretched and slowed enormously. Space and time are malleable. When massive stars dance and merge in the depths of space, they send faint tremors through the fabric of space-time, gravitational waves that ripple outward like the surface of a pond disturbed by a stone. We have learned to hear these whispers of space-time. In giant detectors on Earth, we've caught the subtle stretching and squashing of space itself as black holes in distant galaxies collided and made the very planet quiver by less than the width of an atom. Reality, it turns out, is far more fluid and surprising than our everyday senses suggest. And through it all, filling the backdrop of the cosmos, is that gentle glow from the beginning of time. Once a brilliant flash of newborn light, now stretched to a cool whisper, it bathes the entire universe. It is a cool remnant of the fireball era, a billboard in the sky quietly proclaiming our origins. We are immersed in this ancient light at every moment, warmed imperceptibly by photons that have been traveling for nearly the universe's entire lifetime. The past is never fully gone. It surrounds us, humming softly just beyond our vision. Even in the stillness of a moonless midnight, with the stars glittering overhead, the air around us carries the faint whisper of the Big Bang. Here, on this tiny blue world, orbiting an unremarkable star in the outskirts of an ordinary galaxy, the universe has opened its eyes. We find ourselves alive, aware, and filled with questions inside a cosmos so vast and ancient that our minds strain to grasp it. We feel small beneath the sprawl of stars overhead, yet we are intimately connected to them. The very substance of our bodies was forged in stellar furnaces and spread through space by stellar deaths. The calcium in our bones was forged in the belly of a supernova and cast into the galaxy before condensing into the world that would one day become our home and finding its way into our bodies. The iron in our blood once dwelt in the core of a massive star long ago. It rode the shock wave of that star's explosion, floated through interstellar space, and eventually became part of the dust and rocks that built this planet. The carbon in our DNA was cooked in the hearts of dying stars and released into the galaxy, wandering for eons until incorporated into the cells of our ancient ancestors, and now into us. Every atom in your body has traveled through time and space to be part of you. When we say we are made of stardust, it is the literal truth. We are made of this cosmos. We are built from its history. We are a way for stardust to contemplate the stars, for the cosmos to know itself. With our minds awakened, we have peeled back layers of time and space, determined to understand our origins. We have found that the universe is even more majestic and mysterious than those early sky watchers around the fire could have imagined. We have sent probes to other worlds and seen our planet from afar, a pale blue dot suspended in darkness, realizing how small and precious our home is. We have built great observatories that collect the ancient light from the beginning of time, and particle accelerators that recreate conditions just after the Big Bang. Every question we answer leads to deeper questions, but each discovery brings us a bit closer to the truth of our origins. Through science and art, through myth and mathematics, we continually translate the cosmos into terms we can understand. We create music and poetry inspired by the stars, and equations and theories to explain them, all in an effort to express the inexpressible. In doing so, the universe is writing its story through us. Our art, our science, our curiosity and creativity, they are the universe's way of reflecting on itself. What is the universe? It is an unfinished story, both out in the heavens and within our own minds. It's the totality of all that is, matter and energy, space and time, and also the emergent experiences those give rise to, like beauty and love and curiosity. It is every galaxy that twirls, every star that shines, every life that lives. It's the roar of the Big Bang and the quiet whisper of a human heart pondering the cosmos late at night. It is, in a sense, the universe asking itself what it is. We, tiny motes of consciousness on a small planet, carry the torch of this grand story forward. We are the narrators and also characters in the cosmic epic. In seeking to find our place in it, we find that we are it. We are not separate from the universe at all, but an inseparable part of its unfolding. The universe is inside us, made of us, as much as we are inside the universe. Its story is our story. In the end, the universe is a grand cosmic symphony, and we are a brief but vital motif within it, yet integral to its music. As we live and love, explore and create, we add our own notes to this ongoing composition. The music began long before we arrived, and will continue long after we are gone. But for this fleeting moment, we can listen to it, we can marvel at it, and we can even play our part. Through our ears, the universe listens to its own harmony. Through our eyes, it gazes upon its own magnificence. Through us, the universe feels wonder. As we gaze into the darkness sprinkled with ancient light, we cannot help but feel a profound connection. The atoms of our bodies were born in stars. Our thoughts are shaped by laws that govern galaxies. We are the universe, awake, curious, and able to ponder itself. In our brief lives, in our questions and dreams, the cosmos achieves a form of self-awareness. The story of the universe is still unfolding, and we are chapters in its narrative, co-authors of its next verse. So, what is the universe? It is more than a collection of galaxies and particles and physical laws. It is an experience, an ongoing, mysterious experience that includes the rise of conscious beings who can ask that very question. It is the primordial darkness and the burst of light. It is the weaver of space and time and the tapestry woven. It is the question and the desire to understand. It's the infinity that birthed us and that we now reach for in our thoughts. The universe is the grandest of all stories, the story of everything. And through our questions, our explorations, and our awe, that story continues. The universe is still writing itself through us. Each of us, with our wonder and our creativity, is a means for the cosmos to know itself and to continue its epic. In the final reckoning, the most beautiful creation of the universe may not be a star or a galaxy, but the very capacity to appreciate its wonders. We are the universe's way of marveling at its own majesty. And as long as there are beings to look up at the sky and feel awe, the universe's story will never truly end. Silence, darkness, no stars, no ground beneath your feet, and perhaps not even the flow of time, just an infinite, motionless night. Imagine a void, with no up or down, no sound or motion. In that profound quiet, before anything begins, we find a fundamental question taking shape. What is the dark, yawning space that stretches out in all directions? Not the stars or planets that speckle it, but the space itself. The black canvas on which all cosmic lights are hung. What is space, when it stands alone, empty of all things? Since ancient times, people have looked into the night and pondered the void. Many mythologies begin with a great empty darkness from which creation arises, a cosmic egg in a vast sea, or a formless chaos giving birth to the world. In a way, modern science echoes those old intuitions. We too speak of an initial emptiness that blossomed into the universe we know. We usually imagine space as nothingness, a vacant expanse separating the stars. Even scientists once assumed it was merely an empty stage. In the 19th century, many thought an invisible ether must fill the void, a mysterious medium to carry light. But every experiment to detect this ether failed. Light needed no carrier at all. It moved through pure vacuum. Space, it seemed, could be truly nothing. And yet, if you listen closely to the silence, you may sense something more subtle. The void is not truly void. The darkness is not truly nothing. Space is a presence, an invisible fabric that underlies everything. It is quiet and transparent, so easy to ignore, yet it is real, physical, and dynamic. Space isn't an empty backdrop, but an active, ever-present matrix. It can bend, it can stretch, it can ripple. About a century ago, our picture of space underwent a profound change. Experiments and new ideas revealed that space is not a fixed, unchanging void at all. It can warp and even participate in the cosmic dance. Gravity, we learned, is not a mysterious pull through nothingness, but a bending of space itself by mass. Space and matter interact continuously. Space is like the quiet canvas that holds a painting, or the pause that makes music melodic, an unseen framework that underlies and gives form to everything. Imagine placing a heavy ball on a taut rubber sheet. The sheet stretches and sags under the weight. In much the same way, anything with mass, a planet, a star, a galaxy, presses on the fabric of space. Space curves gently around it. What we feel as gravity is not a pull through emptiness, but the tendency of objects to slide down those curves. The Earth circles the Sun because the Sun dents the space around it, like a large marble sitting on a stretched cloth. Earth is not tethered by invisible strings. It is caught in the Sun's invisible indentation in space-time, moving along a curved path that to us appears as an orbit. In short, mass shapes the geometry of space, and space guides the motion of mass. Even light, which has no mass at all, follows the curves of space. Over 100 years ago, during a total solar eclipse, astronomers noticed that stars appearing near the eclipsed sun were slightly out of place. Their light had bent on its journey to us, detoured by the sun's warped space. It was a dramatic confirmation that space itself, curved by the sun's presence, was guiding the starlight. Today, we regularly use this effect, called gravitational lensing, to observe distant galaxies. A massive cluster of galaxies can act like a cosmic lens, its curved space bending the light of even more distant objects behind it. Sometimes we see a single galaxy smeared into an arc, or even a perfect ring of light encircling a closer galaxy cluster that is acting as the lens. These mirages are the unmistakable signature of space, behaving like a gigantic lens, bending and focusing the paths of light. Through these rings and arcs, we see space itself revealing its curvature to our eyes. If space can bend, it can also stretch. Indeed, the fabric of space has been steadily expanding since the primordial beginning of the universe. Distant galaxies are not just flying away through space. The space between us and them is itself growing. Early observers noticed that the light from remote galaxies is shifted toward the red end of the spectrum, as if the wavelengths have been stretched out. The farther a galaxy, the more its light is redshifted. The straightforward explanation is that space itself is expanding, carrying galaxies apart like raisins embedded in rising dough. Over billions of years, this expansion has enlarged the distances between galaxy clusters immensely. Another useful image is to picture space as the two-dimensional surface of a balloon, with galaxies like ink dots on that surface. As the balloon inflates, the dots move farther apart from each other. No single dot is the center of the expansion. Every dot sees the others receding. Likewise, in our three-dimensional space, every galaxy observes other galaxies rushing away. If we rewind this expansion in our minds, we find that in the distant past, everything was closer together. Galaxies crowd nearer, stars huddle closer. Far enough back, all the matter and light in the universe was crammed into a much smaller volume than today, a state of incredible density and heat. Space itself was compact and blazing with energy. There was a time when the entire young universe was like a hot, glowing fog. Imagine being present in that early inferno. No distinct stars or structures, just a blazing soup of particles and light everywhere you look. An intense white-orange glare filling all of space. As space expanded and thinned out, that searing brilliance faded to a gentler afterglow. Even now, space carries a memory of that fiery beginning. When we point sensitive instruments to the sky, we detect a faint glow of microwaves coming from every direction. This is the afterglow of the primordial fireball, the cosmic microwave background. It is the light from a time about 380,000 years after the Big Bang, when space had cooled enough for atoms to form and for light to travel freely. Since then, those light waves have been stretched by the ongoing expansion of space until they are microwaves, cooled to only a few degrees above absolute zero. Every patch of space is filled with this soft whisper of ancient light. It is almost perfectly uniform and smooth, but has tiny fluctuations, little freckles of slightly warmer and cooler spots, corresponding to minuscule density variations in the early universe. Those slight differences, on the order of only 1 part in 100,000, became the seeds for galaxies and clusters later on. It's as if the walls of the universe still faintly remember their incandescent youth. This ancient light also gives us clues about the overall shape of space. By studying subtle patterns in the microwave background, scientists have learned that on the largest observable scales, space is remarkably flat in its geometry. In a curved universe, those patterns would appear distorted, larger or smaller than expected, much as drawings on a balloon change size when the balloon is inflated. But observations show no such distortion. The angles of those primordial patterns add up just as they would in flat, Euclidean space. For example, in a universe shaped like a 3D sphere, a closed universe, 2 initially parallel beams of light would eventually converge and meet, and traveling in a straight line long enough could, in theory, loop you around to your starting point, just as an airplane circling the Earth arrives where it began. In a saddle-shaped or open universe, parallel beams would diverge and triangles would have angles summing to less than 180 degrees. But our measurements show nothing of the sort. This suggests that space, as far as we can measure, is not curved into a giant sphere or warped into an endless saddle. Instead, it stretches out in all directions without substantial overall curvature. Space is, to the best of our knowledge, flat and likely unbounded, or so vast that it might as well be infinite. It might extend infinitely, or perhaps it wraps around on a scale so colossal we cannot detect it. But within our cosmic horizon, space behaves like an endless level plane. To achieve such vast flatness and uniformity, the universe likely underwent an extraordinary growth spurt at the very dawn of time. According to the theory of cosmic inflation, a fraction of a second, on the order of 10 over 32 seconds or less, after the Big Bang, space itself expanded at a mind-boggling rate, doubling in size over and over in the blink of an eye. In that brief moment, what had been a microscopic region inflated to astronomical scales. A region smaller than a proton might have stretched to the size of a galaxy in an instant. This rapid stretching would have smoothed out any curvature or clumps, explaining why space now appears so flat and even on large scales. During inflation, tiny random quantum fluctuations, little blips of density in the microscopic early universe, were blown up to enormous sizes. Quantum fluctuations inherent to space itself, magnified to cosmic proportions, became the seeds of future structures. Regions of the young universe that had just slightly more matter or energy became, after inflation, entire huge regions with that slight edge. Those minuscule differences, perhaps only a few parts in 100,000 in density, gave certain patches of space a head start in gravitationally attracting matter. As the universe aged, those patches grew into the first galaxies and clusters. In this way, inflation planted the seeds of cosmic structure. The slight differences from one place to another, once infinitesimal, became the blueprint for all the galaxies, clusters, and voids that would later develop. Space, by expanding so fiercely, essentially cast the dice for the universe's future architecture, turning tiny quantum wrinkles into the grand pattern of stars and galaxies we observe today. When this furious burst of expansion ended, the energy driving it did not simply vanish. It transformed, heating the universe with a burst of radiation and particles. In essence, when inflation stopped, space unleashed its pent-up energy, igniting the hot Big Bang fireball that people often think of as the beginning of the universe. From that point onward, space continued to expand, but at a calmer pace, filled with a blazing plasma that would eventually cool into atoms, gas, stars, and galaxies. The rapid inflationary expansion set the initial conditions, and the slower expansion that followed allowed the cosmos as we know it to emerge. Inflation also opens the door to a startling idea: a multiverse. If the inflationary expansion happened in our region of space, it might have happened, or be still happening, in others. Some theories suggest that inflation never completely stops everywhere. While it ended in our patch, allowing our Big Bang and galaxies to form, in other regions space might still be inflating, or might have ended at a different time. Each of these regions could become its own universe, a bubble with its own galaxies, and perhaps even different physical constants. Our observable universe would then be just one bubble in a limitless foaming sea of universes. We have no way to directly see these other bubbles. They lie beyond any light we could ever receive. But the multiverse concept shows how our conception of space may extend even beyond the bounds of our own universe. Space, in this grand view, is an ever-expanding ocean, spawning countless cosmic islands. Whether this is true or not remains speculative, but it stretches our imagination of what space could be, not just the stage of one universe, but perhaps a prolific generator of many. Over billions of years following inflation, gravity worked on the tiny density variations left in the fabric of expanding space, drawing matter into clouds and clumps that would ignite as the first stars and galaxies. Galaxies pulled together into groups and clusters, and these linked up via filaments of gas and dark matter, forming a vast cosmic web. On the largest scale, the universe looks like a spider web or a sponge, dense clusters of galaxies connected by thread-like filaments, with enormous dark voids in between. Those voids, immense bubbles, millions of light years across, nearly empty of galaxies, are the regions that gravity emptied out as it drew matter into the filaments. In other words, most of the universe's volume consists of these yawning voids, with the galaxies tracing lacy patterns along their boundaries. It's a breathtaking structure, the invisible scaffolding shaped by gravity out of the expanding fabric of space, with over 80% of the volume of the universe contained in those silent voids. The lights of the stars and galaxies stand out like glittering nodes, but it is the darkness between them that dominates by volume. Now picture yourself in the middle of one of those cosmic voids, utterly removed from any galaxy. You are floating in intergalactic darkness, light years from the nearest star. Around you, the darkness is nearly absolute. Perhaps a faint, ghostly smudge of a distant galaxy is barely visible in one patch of sky, and another dim glow in the opposite direction. But to your unaided eyes, it would mostly be pure black. The nearest substantial galaxy could be tens of millions of light years away, so far that its light is unimaginably feeble. You are, for all practical purposes, alone in a silent, endless night. This is space at its most austere, a volume of the universe almost entirely devoid of matter. And yet, even here, space is not truly empty. A stray hydrogen atom might drift by now and then, or a thin breeze of particles from some far-off galaxy cluster might waft through. You would also be bathed in the ever-present microwave background radiation from the Big Bang, though you wouldn't sense it without instruments. In this void, you can viscerally feel that space is something real, a vast container with you at the center and almost nothing else around. It's a haunting, beautiful solitude. Such voids are the dark wombs of the cosmos, within which the bright filaments of the cosmic web are suspended. Gravity's architecture, the cosmic web of filaments and voids, is heavily influenced by a form of matter we cannot see, dark matter. Decades ago, astronomers measuring the speeds of stars in galaxies discovered a surprise. In galaxies like our Milky Way, the outer stars orbit the center far faster than expected, based on the visible stars and gas alone. They should have been flung off into space, but they remained bound. It was as if an extra unseen mass was providing the gravitational pull to hold them in. Likewise, galaxies in rich clusters move as though there is much more mass present than we can account for with the observed galaxies and hot gas. And when we observe gravitational lensing by a cluster, the bending of light is far stronger than visible matter alone can explain. All of this evidence points to a vast amount of invisible mass enveloping galaxies and clusters. We call this mysterious substance dark matter. It neither emits nor absorbs light, making it effectively invisible to our telescopes. Yet it outweighs ordinary matter by a factor of about 5. Dark matter forms huge halos around galaxies, extending well beyond the visible stars. Every galaxy, including our own, is embedded in a cocoon of this invisible material. Entire galaxy clusters are swathed in massive clouds of dark matter. Its gravity is what helped pull normal matter into the filaments of the cosmic web in the first place. Without dark matter's guiding gravitational pull, the universe's large-scale structure would have formed much more slowly and differently. We cannot see dark matter directly, but we see its imprint. Space curves around it, and galaxies move under its gravitational influence. Through these effects, the hidden scaffolding of dark matter in space becomes perceptible. Space is quietly filled with an unseen mass that shapes the universe profoundly. In the late 20th century came another revelation. The expansion of space is accelerating. After gravity built the cosmic web, one might expect that over time the pull of all those galaxies on each other would slow the expansion of space. And for billions of years, it likely did slow. But to great astonishment, we have found that in the last few billion years, the expansion of the universe has begun to speed up again. Distant galaxies are receding faster and faster as time goes on. Space is expanding not only steadily, but with an ever-increasing pace, as if some mysterious force is pushing it outward. We give the name dark energy to this unknown cause of cosmic acceleration. Unlike dark matter, which adds gravity, dark energy seems to act as a kind of anti-gravity on vast scales, a subtle pressure embedded in the fabric of space that drives it to expand faster. As space grows, more of this repulsive effect appears, since dark energy is thought to be a property of space itself, pushing galaxies apart with increasing strength. Today, dark energy dominates the universe's energy balance. Roughly 70% of the total contents of the cosmos appears to be this shadowy influence, with dark matter making up most of the rest. The ordinary matter, the stars, gas, dust, planets, and us, accounts for only a few percent. In an ironic twist, the emptiest thing, space, contains the majority of the universe's energy in this form. The silent void has an energetic underpinning that shapes the cosmos. What this means for the far future is profound. As space expands faster and faster, galaxies that are now visible will eventually slip beyond our cosmic horizon, their light stretched and diminished until they vanish from view. In tens or hundreds of billions of years, everything outside our local group of galaxies will have moved out of reach. The universe will appear to whoever remains as an empty void, with only the local galaxies, perhaps merged into one, in view. For example, in about 100 billion years, the galaxies of the Virgo cluster and beyond may be so far that their light never reaches the Milky Way region. After many hundreds of billions more years, even the nearest large galaxy, Andromeda, now destined to collide and merge with our Milky Way long before then, and its remnants would be far beyond detection. The expansion of space will carry all other islands of matter irretrievably away. What will the cosmos look like then? In that deep future, the observable universe will become dark and empty, with only faint whispers of local starlight remaining. Perhaps an astronomer living in that far future era on some distant world would peer into the sky and see nothing beyond her own galaxy. She might point her telescope outward and find endless blackness in every direction. All other galaxies would have faded beyond reach or redshifted into obscurity. She would have no way of knowing that a vast cosmos full of galaxies had ever existed. The cosmic truth we know today, that space teems with billions of galaxies, would be hidden from her by the relentless expansion of space. That future astronomer might conclude that her galaxy was the entire universe, a tiny island adrift in infinite nothingness. For us living in the present cosmos, the discovery of dark energy is a humbling reminder that what we once took to be empty nothingness can control the destiny of everything. The silent space between galaxies turns out to hold a secret power that shapes the entire evolution and future of the universe. Space, the quiet stage, has proven to be the hidden protagonist of the cosmic story. Before we return home, let us take an imaginary journey back through the cosmic expanse. Picture yourself out at the edge of a great cluster of galaxies, where hundreds of galaxies shimmer around you like a glittering swarm. Now you begin to travel back toward our own galaxy. As you move, galaxies drift past, scattered in the vast darkness. You glide along one of the filaments of the cosmic web that leads to the Milky Way, passing other island universes along the way. In the distance ahead, a faint band of light comes into view, the combined glow of billions of stars. Our Milky Way, seen from afar as a hazy, spiral disk of light. You approach it, crossing the immense gulf of intergalactic space. Now you plunge into the outskirts of our galaxy, rushing past sparse outer star clusters and the wispy halo of tenuous gas. The star density increases around you as you enter the Milky Way's disk. Entire clusters of young stars drift by. Great nebulae, stellar nurseries, glow softly in pink and blue. By the time you near the inner regions, stars surround you like a sparkling ocean. You weave through a spiral arm, passing magnificent blue-white giants and red supergiants, skirting around clouds of interstellar dust. In the distance, you spot a modest yellow star, our Sun, coming into view. As you draw closer, you see it is accompanied by planets orbiting in the plane of a thin, flat solar system. You sweep past the orbit of Jupiter, then Mars, and now the blue sphere of Earth appears. At this scale, it is a tiny, fragile-looking bead of blue and white, shining against the blackness. You home in on it, watching its oceans and clouds resolve into clarity. In moments, the planet looms large, its atmosphere a glowing thin shell. You slip gently into that atmosphere, experiencing the rush of air as you descend, and finally come to rest on Earth's surface, back to the soft familiarity of ground beneath your feet. Your fantastical voyage from the end of the universe to our home is complete. Now, having roamed the vast reaches of the cosmos, let us gently return our focus to something more intimate, the space around and within us. We leave the clusters of galaxies and zoom back toward a single galaxy, our Milky Way, and then to a particular star, our Sun, with its family of orbiting planets. Between those worlds stretches millions of kilometers of space, populated only by sparse dust and the thin wind of charged particles from the Sun. Closer in, we see the blue marble of Earth, surrounded by the gauzy blue halo of its atmosphere. From high above, Earth appears as a delicate blue-white sphere hanging in the blackness. Our atmosphere, a thin film of air and cloud, clings to its surface and gradually merges into space. Only a few hundred kilometers up, the air becomes so tenuous that space begins. Beyond that, the sky fades to black. In truth, there is no sharp boundary where space starts. The air just thins more and more until there is effectively none. But effectively, just above the blue sky, the true vacuum of space begins. Only a fragile veil of atmosphere separates us from the cosmic void. There, in low Earth orbit, astronauts aboard space stations witness directly the stark contrast between the bright Earth below and the utter blackness above. They float in microgravity, essentially falling around Earth, immersed in space. When they look up, away from Earth, they see endless darkness spotted with stars that do not twinkle because there is no air up there to flutter their light. The sun shines fiercely without the softening filter of atmosphere, and the divide between day-lit Earth and night-shadowed Earth is a sharp line across the globe. Those astronauts live on the very boundary of space, inside a thin bubble of air in their spacecraft that separates them from the vacuum outside. They often describe the experience as deeply humbling. Above them, an infinite void. Below them, the jewel of Earth with its thin blanket of air. During spacewalks, when they step outside into the vacuum, wearing only a protective suit, they can feel the profound silence and isolation of space. No sound, no breeze, only the distant curve of Earth and the raw, brilliant stars. For them, space is not a theoretical concept, but a palpable reality. They understand in their bones that space is here, around us, an ever-present ocean, just a breath beyond our daily reach. We descend back to the surface now. Picture yourself standing on a quiet night field, looking up at the stars. Although you feel solid ground underfoot and air on your skin, you are as much in space as an astronaut floating in orbit. The space around you is simply filled with a thin mixture of gases, our atmosphere. If you could magically remove all that air, the vacuum that remains would be continuous with the vacuum between the planets and stars. There is no wall or border between space down here and space up there. It is one connected expanse. The same space that stretches between galaxies is present in the room around you, between the walls and among the molecules of air. We truly have never left space. We live at the bottom of a shallow ocean of air, but that ocean is itself embedded in space. People often talk about going into space as if it's somewhere else, but space is already here, step by step. As you climb a mountain or rise in a balloon, the air thins and space reveals itself. Astronauts in orbit are not in a different realm. They have merely ascended above most of the air, into the naked vacuum that was there all along. Space is not distant. It is the backdrop of our existence, even here on Earth. Even our everyday experiences are dialogues with space. Take a breath. You inhale molecules of air that moments ago were scattered across the room, and you exhale molecules that will disperse outward. In doing so, you are stirring the space around you. The air filling your lungs quickly mixes and returns to the atmosphere, ultimately diffusing into the great expanse. In a very real sense, space is the medium through which life interacts with the world. Every movement you make is a displacement in space. Every sound you hear travels to you through vibrating molecules in space. Out in the near-total vacuum beyond Earth's atmosphere, there is no air to carry sound. In space, no one would hear you scream. It is truly silent out there. Every sight you see is brought to your eyes by light crossing space. Space is not an abstract backdrop to life. It is intimately involved in every aspect of our being. Consider even more deeply, you yourself are largely made of space. The atoms in your body are mostly void, their mass concentrated in tiny nuclei, and their size defined by electrons moving through emptiness. If all the empty space in your atoms were somehow removed, you would collapse into a speck far too small to see. And of course, without that space, you wouldn't exist as a living being at all. It is the spacious architecture of your atoms that allows them to bond into molecules, and molecules to build cells, and cells to form a living organism. Thus, space is inside you as much as you are in space. It provides the room that your particles and forces need to operate. We begin to see a pattern from the vast distances between galaxies down to the tiny gaps within atoms. Space is there, quietly doing its work. It provides room for structure to exist, for planets to orbit, for light to travel, for atoms to join and form molecules. The emptiness is not a flaw or an absence. It is an essential ingredient. It allows separation and form. Without the gulf of space within each atom, there could be no distinct atoms and no chemistry, no solid matter as we know it. Without the reaches of space between stars, gravity could not isolate individual worlds where life might arise. Space is the great enabler, the silent canvas that allows matter to take shape and motion to have meaning. Just as a clay pot's usefulness lies in the empty space it encloses, the utility of the cosmos lies in its gaps and hollows. An empty cup holds water. The emptiness within an atom allows it to bond with others. In both cases, what is not there enables what is there to function. And what about space at even smaller scales? Far smaller than an atom, smaller than the tiniest subatomic particle. Here we approach deep mysteries. Physicists suspect that if you zoom in far enough, space itself becomes turbulent and uncertain. On the scale of the Planck length, about 10 to 35 meters, the very concept of distance might break down. Space might dissolve into a kind of quantum foam, with the smooth fabric of space-time becoming frothy and indeterminate. At that scale, according to some ideas, tiny bubbles of space-time could appear and vanish, and geometry itself might fluctuate wildly. Wheeler, a physicist, famously imagined the scene as the quantum foam, a churn of space-time at the smallest scales. Over sufficiently small distances and brief moments, the smooth geometry of space and time could erupt into a storm of random fluctuations. Imagine zooming into what looks like a smooth photograph, only to find it grainy with pixels at a certain magnification. These fluctuations could be large enough, on those scales, to cause significant departures from the smooth space-time we perceive at human scales, giving space a foamy, jittering character when examined ultramicroscopically. With our current technology and understanding, we cannot probe such minute scales directly. Our best theories, quantum mechanics and general relativity, don't play nicely together at this extreme, so we don't yet have a clear picture of what space truly looks like at the Planck scale. It's possible that space-time is not fundamentally smooth. It might be made of countless tiny units or threads. There is no definitive reason that space needs to be perfectly continuous. Perhaps, in a full theory of quantum gravity, space-time would consist of many small, ever-changing regions where space and time themselves blur and fluctuate. It's a mind-bending idea. The familiar continuity of space might, under magnification of 1033, break into a ceaseless fizz of tiny distortions and ephemeral particles popping in and out of existence. Yet black holes are not absolutely black. Quantum theory predicts that the vacuum near the event horizon of a black hole seethes with particle-antiparticle pairs. Occasionally, one particle from such a pair can be pulled into the black hole while the other escapes. To an outside observer, the black hole appears to emit a faint trickle of particles, a phenomenon known as Hawking radiation. Over inconceivably long periods, this process can cause a black hole to slowly evaporate, leaking its mass back out into space. This is another reminder that even the empty space near a black hole is full of activity. The vacuum isn't void at all. Its quantum fluctuations can have tangible effects, bleeding away the black hole's mass bit by bit. In this way, space acts as both giver and taker, swallowing light at the horizon, yet furtively returning energy to the universe through quantum processes. One place where we suspect this quantum nature of space becomes crucial is inside black holes, those mysterious abysses formed from collapsed stars. A black hole is a region where space is curved so extremely that once anything, matter or light, falls in, it cannot escape. The boundary around a black hole is called the event horizon. At that boundary, space is rushing inward at the speed of light, like a waterfall of space-time cascading into the hole. If you approach the horizon, time slows relative to the outside world, and the pull of gravity, the curvature of space, becomes overwhelming. To a distant observer, you would appear to slow and dim, never quite falling in, as your final light waves get stretched and weakened, a strange visual consequence of the way space and time warp. Beyond the horizon, all paths lead further inward, deeper into the hole. As you fall inside a black hole, you would experience space rushing you inexorably toward the center. According to general relativity, at the very center lies a singularity, a point of infinite density where space and time, as we know them, ends. In truth, this singularity is likely where our current understanding fails. Gravity is so extreme and the scale so tiny that quantum effects should dominate. Here, the smooth fabric of space might tear or blend with the quantum foam. The distinction between space and matter could blur. We don't yet have a theory of quantum gravity to tell us exactly what happens in such an intense intersection of the very large and the very small. Does space cease to exist as a meaningful concept at the core of a black hole? Are there atoms of space-time or quantum threads knitting things together beyond our view? We simply don't know. The laws of physics as we have them break down in these conditions. Physicists have proposed bold ideas to reconcile these deep conflicts. One radical suggestion is that space and time might not be fundamental at all, but rather emerge from something more basic and abstract. Some research hints that quantum entanglement, the ghostly interconnection between particles, may knit together the fabric of space itself. In certain theoretical models, the geometry of a region of space can be described entirely by the information, the entanglement connections, on its boundary. This is known as the holographic principle, suggesting that our three-dimensional space might in some way be a projection from information encoded on a distant two-dimensional surface. It's as if space could be woven from quantum threads of information. Another idea is that space-time is composed of tiny, discrete units, sometimes envisioned in approaches like loop quantum gravity, so that on the smallest scale, space is more like a woven lattice or network. These concepts are still speculative and hard to test, but they share a poetic point. They hint that space, for all its apparent continuity, might be an emergent illusion, like a tapestry that looks smooth from afar, but up close is made of fine threads. If so, there could exist degrees of freedom or building blocks of the universe more fundamental than space and time. What is space, truly? It may be that our familiar space is just the visible frosting on a much deeper reality. Facing these profound questions, humanity has responded by inventing clever ways to probe the nature of space. We have built powerful telescopes that peer across billions of light years, effectively allowing us to look back in time and see the young universe when it was filled with hot plasma and newly formed galaxies. We have launched observatories above our atmosphere to measure the cosmic microwave background with exquisite precision, mapping its faint ripples to decode how space expanded and what it contains. We have devised experiments on Earth to test the nature of the vacuum. For instance, sensitive laboratory apparatus has confirmed the Casimir effect, detecting the slight pressure of vacuum fluctuations pushing two plates together. We smash particles together in giant accelerators, momentarily concentrating tremendous energy into tiny volumes of space, to glimpse how nature behaves at the highest energies and smallest scales. This endeavor led to the discovery of the elusive Higgs field that permeates space and endows particles with mass. We have even detected the subtle ringing of space-time itself using gravitational wave observatories like LIGO. These giant laser interferometers can sense when space stretches and squeezes by less than a trillionth of a centimeter as a gravitational wave passes. The first such detection, in 2015, came from two merging black holes and was heard as a faint chirp, literally the sound, after conversion, of space briefly vibrating from a cosmic collision. Since then, we have caught multiple cosmic events via gravitational waves, black holes swallowing each other, neutron stars colliding and sending tremors through space. It's a completely new way of listening to the silent universe, using space itself as our messenger. We have also physically journeyed into space, albeit only a small distance so far in cosmic terms. Our robotic probes have ventured beyond the planets, sampling the environment of space directly. The Voyager 1 and 2 spacecraft, for example, have traveled beyond the influence of our sun's solar wind and entered interstellar space, the space between the stars. They confirmed that even the emptiest regions of our galaxy are not entirely empty. They contain traces of very thin plasma, ionized gas, and high-energy cosmic rays. Voyager 1, now over 23 billion kilometers away, is humanity's farthest messenger. It is sailing through the cold, silent void, reporting back that even out there, far from any star, there are a few atoms per cubic centimeter and faint whispers of magnetic fields and radiation. Its journey reminds us that space is not a distant void we go to. It's the ocean we've always been swimming in, now stretching out to greater and greater depths. We are not outsiders to the universe's expanse. We are an integral part of it. We move through space. We depend on it. We are composed of it. In a sense, we, conscious beings, are space's way of observing itself, the universe contemplating its own vastness through our eyes. From the space between galaxies to the space inside your chest, it is one continuous fabric. The next time you gaze up on a clear night and marvel at the darkness between the stars, remember that that darkness is not empty. It is the same space that cradles you, extending through and around you always. We tend to think of ourselves as down here and space as out there. But in truth, we have always been in space. From the moment of our birth, we have been enveloped by space. Space is not a distant domain only astronauts visit. It is the vast, subtle medium in which we live and breathe. When you look up at the night sky, you are looking into an extension of your own surroundings. The air ends not far above your head, and then space continues, unbroken, to the ends of the universe. So, what is space? It is not a mere nothingness, not a sterile void. It is the gentle scaffolding that holds all of creation. It is a medium that can bend and ripple, a vast field that carries light and nourishes the formation of stars. Space is the silence that allows the music of existence to be heard. It is the canvas on which the galaxies are painted. And yet the canvas itself has texture and influence beyond what our eyes see. Space is the invisible architecture of the universe, the foundation that connects all things. It is often said that nature abhors a vacuum, but in truth, nature uses the vacuum, space, as the foundation for everything. Without space, there would be no room for light to travel, no separation for objects to exist apart, no time for events to unfold. Space is not the absence of things. It is the presence that allows things to be. It is the very possibility of anything and everything. As our journey through darkness and light comes to an end, we return to that initial quiet question and find a profound answer. Space is not an emptiness to be feared, but a presence to be revered. It is the quietly fertile nothing that makes everything possible. We float in it. We are made of it, and we are forever embraced by it. The invisible architecture of the universe surrounds and sustains us. Space is the darkness that cradles the stars, the silence that gives meaning to sound, the stillness that makes motion possible. It is the vast, living fabric in which the story of the cosmos and our own story is written. Space is the womb of the universe, the canvas of creation. It is not an absence, but the gentle yet all-encompassing presence that allows all things to be